Okay, let's begin the second day schedule of the 45th CAST International Symposium on Periods of Automorphic Forms. The first speaker of day 2 is Professor Akshay Venkatesh at the School of Mathematics at the Institute for Advanced Study. His research interests are in the fields of counting, equidistribution problems in automorphic forms, and number theory. In particular, representation theory, locally symmetric spaces, ergodic theory, and algebraic topology. In 2018, he was awarded a Fields Medal for his synthesis of analytic number theory, homogeneous dynamics, topology, and representation theory. His other awards and recognition include Ostrovsky Prize, Infosys Prize, Sestra Ramanujan Prize, Salem Prize, Simons Investigator, Packard Fellowship, Sloan Fellowship, and Clay Math Research Fellowship. He was on the Mathematical Sciences jury for the Infosys Prize in 2020. Now, the title of his lecture is Hamiltonian Spaces and L Functions. Please join me in welcoming Professor Venkatesh. The floor is yours.
Okay, thank you, Sugwoo. Can you see my screen share? Yes, okay. All right, so I wanted to thank the organizers for putting together this nice workshop. I hope I'll have the chance to come in the future to Korea in person and give some lectures and meet some of you. I've met many young, talented Korean mathematicians, and well, perhaps soon we can meet each other again. Okay, so I'm talking, it's about continuation of Yanis's lecture. Okay, so it's a Hamiltonian spaces and L functions, and everything is joint work with David Ben-Zvi and Yanis Sakalaridis. Okay, so what we're talking about today, what we're trying to understand are these period formulas in the theory of automorphic forms. And these formulas equate, on the one hand, you take an automorphic form and integrate it over something. Okay, it may be over some submanifold, maybe against some theta series. And there's a huge class of formulas that wherein such an integral is equal to an L function. Okay, so let me just comment on this squiggly sign. I put it in red just to remind me. So throughout this talk, I'll use this to mean the formula is true up to a constant which we understand precisely. And I'll talk at various points about the constant, but I don't want it to distract us. So this sign means equality up to a understood but often interesting factor. Okay, so I want to, first of all, let me just say one word about why such things are useful in number theory. And basically, there's kind of a bottleneck in number theory that there's very few ways to rigorously access L functions. Okay, if you have the Riemann zeta function, you can analyze it by hand, but most other L functions, we really have no way to access them except through such formulas. Okay, so over number fields, for the most part, almost everything we know about L functions comes from such a formula. Maybe one of quite a simple nature, but there are very few other ways to access L functions in our present understanding. And so for the purpose of this talk, I want to kind of adopt this terminology, really kind of distinguish the two sides. On the left-hand side, we have an automorphic period. And I want to just loosely think what an automorphic period is something that extracts a number from an automorphic form. Okay, it takes an automorphic form, spits out a number. On the right-hand side, we have a spectral period. So this is a non-conventional notation, but it just means the parallel thing on the other side. It takes in a Galois representation and it spits out a number. That's what I mean by spectral period. So the kind of basic example of that you should have in mind is an L function. Okay, an L function is, it takes in a Galois representation, and you evaluate at a point, it gives you a number. Okay, so for us, we're looking at these period formulas, which are a matched pair of an automorphic period and a spectral period. It's a pair of these that match in the Langlands correspondence. Okay, so let me say before I get going what I'm going to try to communicate in this talk. And by the way, I'm very happy to hear questions, but I'm not looking at the YouTube streams. So please, Sugwoo or Youngju, just shout out whenever people ask. So G and G check are dual reductive groups. And we'll be a little more specific in a moment. But what I'm going to explain in this talk by example is a duality. Okay, and this duality switches. You start off with a period for identity for one group. It relates an automorphic period for G to a spectral period for the dual group. And we're going to see there's a duality that switches this with an identity, a similar identity for the dual group. Okay, where the roles of G and G check are switched. Now, there are a lot of periods which has been around for a long time. And I think maybe the reason this wasn't observed is that it really becomes visible or clearly visible when you recast the whole story in terms of Hamiltonian spaces. So that's Yanis in his talk has explained about this on the automorphic side, and I'm going to do the same thing on the spectral side. And one of the payoffs of this is that we will see there's this duality in the whole theory of periods. So the kind of we would like to propose this duality is really it's a fundamental organizing principle for the theory of periods. Okay, there's not just this long list of examples. This duality organizes it just as the Langlands duality organizes the theory of automorphic forms. Of course, you know, we would also like to get new things out of this, and I'll say at the end of the talk some of the things we would like to probe next. Okay, and I also hope this is really an example-based talk, and I've oriented this at people who have some familiarity with, you know, maybe you've seen some example of an automorphic period. But hopefully, if you have a little background there, you may be able to go after the talk and compute the dual example for your favorite period. Okay, so let me run through the notation. G and G check are dual reductive groups, and I will take them over Z. So this question came up yesterday. I'll take them, the split forms over Z, so that I can talk about their points over any field. Okay, clearly there should be a version of this whole story without that, but we haven't thought about it, and this will simplify our life. F is a global field, and I said it's preferably a function field because I'm often, it's not a real issue, but I often don't want to say things about Archimedean places. And square brackets G is the space on which automorphic forms for G live. Okay, so that is depending on whichever you feel most familiar with, the adelic quotient, G of the finite adel, G of the adels of F, or the rational points, or you could take the associated locally symmetric space. Or over a function field, you could think of the set of isomorphism classes of G bundles on a curve over a finite field. Okay, it's the space where automorphic forms live. Phi will be an automorphic form. So what that means, it's a function on that set, which is an eigenfunction of all the Hecke operators. And I say preferably a cusp form. I mean, some of the statements I make will be accurate only for cusp forms. But I'll be a little sloppy about this. And finally, this kind of central thesis of the Langlands correspondence is that when you have an automorphic form, it should have an attached Galois representation. And so the exact rigorous implementation of this depends on the situation you're in, but it always takes the general form of a homomorphism from some form of the Galois group of F to the dual group. Okay, so for example, if we were working over a function field, this is known in great generality now by the work of Vincent Laforgue, and the group would be the vague group of F, and you would have an L-adic representation. If it's a number field, we don't have a good general definition for gamma F, but there are kind of standard ways to get around this and act as if we did. So we'll proceed in this way. So phi is the automorphic form, rho phi is the attached Galois representation. So I want to start, as I said, this talk is really about the spectral side. Spectral means that is, the side which has to do with Galois representations. But there's a very symmetric story going on here. So let me just begin by recalling one concept on the automorphic side. So recall, if you have a G variety X, a thing with the G action, it gives you an automorphic period. So okay, what it gives you is a function on your automorphic space, square brackets G, and I'll describe this function in a moment. And that gives you an automorphic period because any automorphic form, you just take the L2 pairing with that function and that gives you a number. Okay, so this function theta x extracts numbers from all automorphic forms at once. And this was defined by Yanis. Let me just repeat it. In the simplest, well, there's a setting you can say it in words, which is when the everywhere unramified setting over a function field, it just counts the sections of an associated X bundle. So over in the function field case, this automorphic space is classifying G bundles. If you have a G bundle, you can make an X bundle. You just take the transition functions for that G bundle and you use them to glue copies of X. And now you have something that some algebraic object that maps down to the curve. You take the number of sections. That's what it is in the function field case. In the number field case, it's given by this maybe more familiar expression of Poincare series. You start with the Schwartz function on the Adele points of X, and you average it over rational points and pull it back to the group. Okay, so that's a very classical construction. There's a good story of how to choose the Schwartz function, which I won't go into, but the idea of making automorphic forms like this was already done by Poincare in the 19th century. Okay, so this gives you a class of automorphic periods. That is, each G variety in this way gives you a way to extract a number from an automorphic form. For a general variety, this number is probably not something which is terribly meaningful. Okay, so but for a special class of varieties that are not too large in some cases, this often these automorphic periods are related to L functions. And as discussed by Yanis, we would like to go beyond this. We would like to look at a larger collection of periods than just these. And for this reason, one sort of enlarges from varieties to Hamiltonian spaces. Well, Yanis talked about that, but let me just mention some examples of periods which are not adequately captured, which are not encoded. Periods of interest, automorphic periods of interest that are not encoded by a variety. Okay, well, the first example is Fourier coefficients. We want to take one of the most basic things one does with holomorphic modular forms. You take a Fourier coefficient, which is called a Whittaker type period, but it's not attached to a variety in the sense I said above. However, it is perfectly well attached to a Hamiltonian space. The second example I want to give is the theta correspondence. Again, Yanis talked about that. Let me just mention that usually we don't think of the theta correspondence as part of the theory of periods. We think of it as a correspondence. That is, it takes in an automorphic form for one group and spits out one for another group. But the way that correspondence works is these two forms match when some period is non-vanishing. Okay, that's the definition of the correspondence. A form here and a form here match up when you stick them into some period and you get a non-zero answer. So you can think of theta correspondence in this sense as a study of a period where you have forgotten all information except whether the period vanishes or doesn't vanish. Okay, so but you can ask about the value of the period. It's an interesting thing. And as such, the theory of theta correspondence is part of this broader story of automorphic periods, but not attached. It doesn't come from a variety. It comes from a Hamiltonian space. So varieties index an interesting subclass of periods, but not all those of interest, of automorphic periods. This whole discussion was on the automorphic side. Okay, so this talk, we are going to have essentially the corresponding discussion on the spectral side. Okay, the same thing has happened on the last slide. We're going to discuss on the spectral side. First of all, we will take a variety X check on which the dual group G check acts, and we'll explain how it indexes a spectral period. All right, so from X check, we will get a way of extracting a number from a Galois representation. And we will explain why this is a useful way of thinking. Okay, it's just a definition, but it will make manifest this symmetry. And then, just as on the automorphic side, not all things of interest come from varieties, and we enlarge this to include Hamiltonian spaces. So before I sort of start on details, let me just give you a little bit of context. Some of this was already mentioned by Yanis. So the study of periods in automorphic forms is an old and enormous subject. So as Yanis mentioned, you could argue it's present in the work of Riemann, and it's clearly recognizable, in a form we can relate to in modern terms in Hecke and the work of Hecke and Rankin and Selberg in the late 1930s and 1940s. Then, another big advance came in the late 70s when Jacquet, Piatetsky, Shapiro, and Shilaika generalized these integrals of Hecke and Rankin-Selberg from GL2 to GLN. And I think then the floodgates opened, and there was a huge amount of work constructing interesting and often very intricate and curious examples of these period identities. Okay, so there's too much of it to review. We'll see examples as we go, but it's a large and beautiful field. So the kind of starting point for, I think, some of the ideas leading into our current work was Yanis's PhD thesis, where he tried to make unified statements of periods to study in some unified way the automorphic periods attached to spherical varieties. Okay, I haven't defined spherical variety, but it doesn't matter for this talk. And then in our book, Yanis and I wrote a book where we tried to systematically relate these kind of questions about global automorphic periods to local harmonic analysis, in particular L2 harmonic analysis, the Plancherel formula. And after writing that, I think we became convinced, just for the purposes of harmonic analysis, that we shouldn't be thinking that the cotangent bundle of X was more fundamental than X. And let me just remind you, a Hamiltonian space is, it's a symplectic G variety with some extra structure. And the basic way from a variety you get a Hamiltonian space is you take its cotangent bundle. Okay, so for the purposes of harmonic analysis, we became convinced that the cotangent bundle was more fundamental. And then in 2017 to 2018, we started to work with David. I mean, I think David was at some distance from us mathematically, but I think David understood something very important that we didn't, which was that Hamiltonian spaces are also important on the spectral side, on the side of the dual group. And one way you can see that from the point of view of geometric representation theory is once you start to study these things, you see there are quantizations around which suggest the existence of symplectic structures as a kind of limit. And finally, there's a rich and closely related discussion in the physics literature. So this is a small part of what is studied in the theory of boundary conditions in quantum field theory. So David will discuss that. And I've found that it's a useful organizing principle for thinking about a lot of this. Okay, so I'm going to start on we're first going to index some, we're going to talk about how to get a spectral period from a variety under G-check, and then the same discussion for Hamiltonian space, and then we'll draw some conclusions. Okay, are there any questions?
Well, not on YouTube for the moment, but I guess you're going to discuss examples later in your talk, right?
There's an example waiting on the next slide.
Okay, good.
Yeah, but please interrupt me. Okay, so let's do an example. Yeah, so the way we this is going to be completely by example. We're going to look at some examples and see how they suggest some definitions. Okay. And I should say, in our paper, we try to make a more formal theory, but for the purpose of this talk, I'm focusing on examples. Okay, so this is a very interesting period on the even general linear group, or let's say PGL to avoid some center. It's considered by Jacquet and Shilaika. And this period is as follows. They take a cusp form on GL2n, and they do the following integral to it. First of all, you take a Fourier this matrix, and I hopefully you can see my cursor. Can you see the M highlighted? Yes. So oops, these are n by n blocks. Okay, this G is an n by n matrix, M is an n by n matrix. So this is a 2n by 2n matrix. You take a Fourier coefficient over this M variable. Okay, so you're integrating over M, but you're putting an exponential oscillating character there. Then you integrate along the block diagonal matrices with the upper and lower things equal. Okay, so that thing is called the Jaeho-Haan period, and they analyze it as part of something a little more general. And they proved the following. So they proved that it is 0 if the parameter of phi, so let's assume this phi is cuspidal, okay, for this statement. If the parameter of phi is not symplectic, then this is 0. So what that means is, okay, the parameter of phi is valued in the dual group, which is SL2n. And to say it's symplectic means it can be conjugated into SP2n. Okay, equivalently, it's symplectic when it preserves a skew symmetric form. So if it's not symplectic, the answer is 0. If it is symplectic, the answer is this L function. Okay, it's the exterior square L function. You take, so it's not the L function attached to the symplectic, the 2n dimensional representation that you have, but rather you take its exterior square. Okay, now when you take the exterior square of symplectic representation, it contains an invariant line from the symplectic form, and you remove that, and that's the meaning of sub-0, this subscript 0 here, and you evaluate that L function at 0. Now, they don't phrase, in a number field case, for example, you don't have this parameter, so they phrase it in an equivalent way. But if you have a Galois parameter available, this is how you would formulate.
Excuse me, Akshay?
Yes.
So in the case that it vanishes,
yes.
So that can't be interpreted in terms of a vanishing of an L function of any sort?
No. It's just 0. There's no L. It's right. It's 0 for, in fact, almost for representation theoretic 0. There's no L function that is vanishing. That's for forcing this. Good question.
But are there also situations where you get L derivatives?
L derivatives are related to kind of versions. Okay, there's in some cases, along with this story, there's a parallel story involving derivatives and heights. Yeah. So typically you get the same L function, but differentiated. Okay, but I won't say anything about it.
But are you thinking, but this is more, what you're saying is more general than, say, Gross-Zagier type of stories, I guess, right?
So Gross, you mean, right, there are more examples than Gross-Zagier. So the story I'm saying often has a parallel incarnation involving derivatives.
Okay, that's right.
Yeah, but no, certainly not always. In some cases when you can have, yeah. Okay, so it's the meaning of the word symplectic I just said. There's a small technical point, which, well, it's not a technical point, but I don't think I won't dwell on it too much. An automorphic form, I said, is something which is an eigenfunction of the Hecke, all the Hecke operators. For GL, for general linear groups, knowing the Hecke eigenvalues normalizes it up, but spins it down uniquely up to scaling. But of course, you have an ambiguity on the left-hand side as to how to scale the form. So you have to normalize it to make this, to make a reasonable formula of this type. Of course, I haven't told you the constants, but no matter how you write a formula, you have to have some way of normalizing it. The standard way to do it is to normalize it by the Whittaker model. That is to say, you take phi so that its first Fourier coefficient is 1. I'll say something more about this normalization issue later, but don't pay a lot of attention at the moment. Okay, so now let's examine the shape of this answer. There are two pieces of data that control it. Okay, first of all, there's an issue of whether it vanishes or not. That has nothing to do with an L function. So as Minyoung, that was the point of Minyoung's question. Okay, the vanishing or not is determined by a certain subgroup, the symplectic group. The thing vanishes unless the Galois representation can be conjugated into that subgroup. And so this subgroup, not just in this example, but other examples, I will call G check sub X. Okay, that's meant to hint, it's the subgroup of the dual group, which is distinguished by the period. And in Yanis's talk, he called this G check sub M. Sorry, I should have changed it to match that. But okay, this subgroup tells you when the period is non-zero, but nothing else. When it's non-zero, you can then further ask, what is it? The answer is an L function, but you want to know which L function. And that's specified by giving a graded representation of the subgroup. Okay, the representation here is the exterior square with this line removed. The grading tells you at what point to evaluate the L function. So here you evaluate at 0, so it's the exterior square in degree 0. Okay, so this is the Jaeho-Haan formula. We can pause briefly to admire it. It's a very beautiful formula. So let me notice something about this. Okay, there are two pieces of data here, and this is the typical paradigm in which, in the past, I think we've thought about periods. There's two questions. When is it non-zero? That's answered by a subgroup. What is it? That's answered by representation. But there's an interesting piece of redundancy between these two data, which is that the representation that you see is isomorphic to the quotient of Lie algebras. Okay, so you can easily check this. The quotient of Lie algebras as a representation for this symplectic, the quotient of the SL Lie algebra and the SP Lie algebra is actually the same as that representation W. Okay, so that's not an accident. It's an important feature. Let's go to another example. My second example is simpler than the first one, but I put it second because I think it's so simple that one can get a little confused by, it's a little bit degenerate in some ways. I'll take the group to be SL2, so classical modular forms, and X to be the affine 2 space with the standard action of SL2. So the resulting function theta X is something that in some variant is discussed in every introductory book on modular forms. Okay, one word for it is the pseudo-Eisenstein series, but this construction is the basic way of making simple modular forms for SL2. Now, this guy, as the name pseudo-Eisenstein suggests, it's some sort of combination of Eisenstein series. It is orthogonal to all cusp forms. Okay, so the automorphic period is 0 if you are a cusp form. But there are things besides cusp forms, and those are you can pair this also with an Eisenstein series. And this computation is a little bit confusing to do, but right, so I'm working on the group SL2. So an Eisenstein series is one whose Galois parameter is reducible. The dual group is PGL2, which means I can twist it to be of the form chi plus 1. And if you so twist it, you will you do the computation and you find that the answer is basically the L function of chi times the L function of chi inverse at 0. But you find a strange thing in this computation, which is that you find somehow two copies of that answer. There are two things you have to compute, and they happen to be equal. They're both the same L function. So you get an extra factor of 2. And of course, that's meaningless because I haven't told you what this constant is. But if you normalize this correctly, you'll get exactly a factor of 2 in front. Okay, so this is an example. I'm selecting some pieces from this constant that are more important in the story. So there's an interesting factor of 2, and if it comes in the end from the functional equation of the Eisenstein series. Okay, so let me reformulate this in the same terms that I did on the previous slide. There is a group that tells you when the period is non-zero, and here it's just a torus. Okay, because what this says is your period is 0 if the Galois representation can't be made diagonal, if it's a cuspidal. And otherwise, it's non-zero, and which one it is. Let's ignore the factor 2 for a moment. Okay, that will come back in a moment. The L function in question is associated with this representation of GM. Okay, it's chi, it's the L function of chi times the L function of chi inverse, which means you take the standard representation of GM plus a copy of its dual. Okay. And yet again, this is a much, much simpler example, but you will notice this same coincidence as you had on the previous one, that the representation that occurs is the quotient of Lie algebras. All right, so now let's take these two examples and reformulate the answer in a uniform way. Just these two examples, but using this coincidence, okay? Because there are two pieces of data, but so one determines the other. So maybe we don't need two pieces of data. So, okay, just let me repeat what they are. Okay, so for any period, at least that encodes an L function, you get these two data pieces. One is a subgroup of the dual group that tells you when the period is non-zero, and a representation of that subgroup that tells you which L function you actually get. All right, so now we are going to sort of use the redundancy that we just saw to discard this in favor of a more compact formulation. So the condition that a Galois representation can be conjugated into this dual group, check GX, is the same as saying it fixes a point on the quotient space. Okay, if I have a subgroup of, if I have anything inside a group, it can be conjugated into a subgroup exactly when it fixes a point acting on the quotient of the group by the subgroup. And here you notice something. In the first example, there are two. If you have a representation, an irreducible representation into SL2N, it can be made symplectic in only one way. Okay, that's Schur's lemma. If it fixes a skew symmetric form, it only fixes one. So it only has one fixed point on the quotient space. In the second example, if you have something going into PGL, a representation into PGL2, and it can be conjugated into the torus, it can be done in two different ways. Okay, it fixes 2 points on the quotient space coming from the torus, and then the vial gives you 1 point from the conjugation of the torus, and then you can apply the vial element to it. So that's nice because there was also a factor of 1 or 2 in front of the L function that I mentioned. And so using that observation, you see that these two examples you can rewrite in this uniform way. The period of the automorphic form on one side is a sum of L functions. And in our two examples, the first example is one L function, in the second one there's two. And in the second example, they both have the same value, just a constant 2. But the sum is taken over this quotient space, check G mod this subgroup check GX. It's taken over points that are fixed by the Galois representation. Okay, so here imagine, you know, if, for example, if you're dealing with an L-adic representation, you would have to work with the L-adic points of this. But so I'm being sloppy about which field we're working over. So if there are no fixed points, you're not conjugate to this and you get 0. Otherwise, you get a sum over fixed points, and each fixed point contributes a copy of the L function associated with the tangent space. Okay, so I'm assuming in this discussion we have discrete fixed points. So each fixed point, once you have a fixed point, the Galois representation acts on the tangent space. It's a linear representation, and you can now make sense of its L function.
Excuse me, Akshay.
Yes.
Do you, in the L-adic case, do you take QL fixed points or QL bar fixed points?
We should take QL bar fixed points if you're working with that. Yeah.
Also, in your first example, did you say the Galois representation is irreducible?
Okay, so in the first example, if you were, the thing I said is correct for a cusp form. If you were dealing with Eisenstein series, the answer becomes complicated. Okay. However, the formulas I say will remain valid there. But yeah, so nothing essential goes wrong, but both sides will be more complicated. Okay, so this is oh yes, and the other point, so the other coincidence I'm using in this formula is that the tangent space is the quotient of Lie algebras, which was the same as the representation appearing in the L function. Okay, so these two examples can be rewritten in a common way, and that motivates a definition. Okay, so this right-hand side is some gadget which really depends only on the space, check X. Okay, it depends only on the quotient, check G mod check GX as a space under the dual group. So let's call this thing the spectral period attached to check X. Okay, so if I take any space at all under the dual group, doesn't have to be homogeneous, I can make sense of the analog of this, at least when you have isolated fixed points. You take a Gauss representation, you take all its fixed points, and you add up the values of L functions at the tangent spaces. Right? This may seem like a priori, it seems like a strange thing to do. We'll see in a moment why it's very natural. But okay, so that's my definition. That's a spectral period attached to a variety on which the dual group acts. Okay. And now you have this definition. You find by looking at examples that many period formulae can be rewritten in this form. Okay, for some group, there'll be a period, and the answer can be encoded in this way. It's the spectral period attached to some simple space on which the dual group acts. Okay, so let me give you some examples, and then we will discuss why this formulation is advantageous. Okay, well, maybe I'll just list, here are a few examples. Maybe one I want to highlight is the third one, which is theta correspondence is an example of that, and we'll come back to that example. Yeah, so in each of these cases, the last two are written in blue because the space check X is not homogeneous. Okay, it has more than one orbit, but nonetheless, the formula is valid. Okay, so the motivation came from examples where in the two motivating examples, this check X is homogeneous, but once you have the formulation, you find that it applies very well also in non-homogeneous examples. I should say many, but certainly not all. Okay, certainly not all period formula of interest, and that's, we're going to come back to that point in discussing Hamiltonian spaces.
So
okay.
In the first example, are we talking about the constant terms of Eisenstein series?
Yes. Yes. So this is an easy example to compute, right? It's but all I'm saying is that if you look at it, it has formally exactly the same form.
Yeah, but then maybe I may not be remembering correctly, but one typically sees some quotient of L functions.
Right. So there's a question of how you normalize, right? So if you take, I'm using Whittaker normalization.
Mm-hmm.
So there's also a reciprocal of L functions inside the first Fourier coefficient. And when you divide it out, this issue goes away. Yeah.
I see.
Excellent question. Yeah.
Actually, I think you also originally worked on the space A2 to construct your pseudo-Eisenstein series, which means that the Eisenstein series are normalized. So maybe the constant terms are normalized and you don't have the denominators.
Okay, let's not get, wait, unless I said something wrong, let's not dwell on this because it's confusing. There are multiple versions of the Eisenstein series, I think, as Yanis is saying, it's normalized or unnormalized. I think it'll be, I don't think I said anything wrong. So if no one is confused, maybe I'll go on. But Sugu, did I answer your question satisfactorily?
Yes, yes, you did. Yeah. Thank you.
Maybe I just say one more thing. The point is there's a sum over the Weil group when you have a constant term, and that will be coming from the Weil group's worth of fixed points on the other side as well.
By the way, can I ask a question from YouTube?
Please, please.
By Peter Humphreys.
Hi, Peter.
What is X check for the Rankin-Selberg for U2n plus 1 times restriction of scalars from F to E of GLN, or for SO2n plus 1 times GLN?
So for the first question, we have not studied field of rationality issues. So I think, so we understand only the clearly only the split case. I presume that there won't be a huge difference if you take a different form of the same period. So that's a form of the Rankin-Selberg. So I assume there'll be some L group formalism to handle it, but we haven't studied it in detail. The second one, I don't know off the top of my head, but we can try to compute it.
And can I ask one more question?
Yeah, please.
From Wansu Kim. Is it possible that the graded representation W has more than one grading?
Oh, yes, I'll give examples. Yes, so you might be disappointed. There will be examples. The W can be interesting. We just haven't seen examples yet. Yeah.
And that's it. Thank you.
Okay. So, all right, now let's emphasize this. At this point, we have simply reformulated things. All the bullet points here are, okay, they're elegant and compact reformulations, but they're just a different way of writing these formulas. So I want to dwell a little bit on why this is a useful way of thinking, okay? So I'm saying we can rewrite these period formulas, or many of them in this form, where you have an automorphic period, maybe attached to some space X, or more general. On the right-hand side, you have a spectral period, which we're now indexing by a space X check. Okay, now I think the most convincing demonstration that this is a useful way of thinking is that you can swap this role of the two sides. Okay, so I have now in the formula on the top of the slide, I have on the one side G acting on X, on the other hand, G dual acting on X dual. But I can put them on the opposite side. I can put G dual and X dual on the automorphic side and G and X on the spectral side. And you find that you get a completely new period. Okay, so for example, in this case, we did SL2 and A2. The dual side was PGL2 acting on PGL2 mod GM. So now we can put this on the automorphic side. So we're looking at automorphic forms on PGL2. We're looking at the period indexed by this, which is simply the Hecke period, the integral of the modular form over a torus. And we're saying this is equal to the spectral period indexed by A2 as an SL2 space. And all that means is if you take a cusp form, it fixes only the origin and you get the standard L function. Okay, it's the standard L function because it's the two-dimensional representation of SL2. Now, notice, okay, so I'm saying if you believe in this being a duality, this is a prediction of the duality. I didn't have to do a separate computation as to which L function I would get. I could simply look at this period and it predicts that this dual period takes the value of the L function. Okay, and as you can imagine, that becomes more interesting in more complicated examples. We expect that the fudge factors here are all of local nature. Okay, so first of all, so as I said, there was this 1 or 2 factor in the examples I gave. So that is captured by the sum over fixed points. Next, there are some factors that can be kind of thought of effectively by kind of doing a unitary normalization, something analogous to the way you unitarily normalize Eisenstein series. And if you do that carefully, which I haven't done in this talk, but we can do it, then we expect that the remaining factors are of local nature, meaning that they're 1 in it's equal to 1 in the everywhere unramified case. And there's some understanding, of course, in the theory of periods, how to handle these local factors at ramified places. Okay, what if the fixed point set is infinite? Okay, this is an issue that's related to poles of the L function. This tends to happen at points where the L function involved has a pole. The formula remains valid as far as we've checked with a suitable regularization on both sides. And here it becomes, for example, it's sometimes advantageous to look at the geometric theory where both sides are traces of Frobenius on some vector spaces, and you can ask to check that the vector spaces are isomorphic even if the traces are infinite. Okay, they're isomorphic as Frobenius modules. So this is, we haven't studied this in great depth, but as far as we've probed it, it seems to be valid at those points also, but with suitable interpretation, so for the purpose of this talk, we will only consider cases where the fixed point set is discrete. Okay, so there's one other point I want to make. And for this last one, I don't want to go too far into geometric Langlands, but there's one, I think, feature that's quite beautiful, which is that the two sides of this formula seem of rather different nature. Okay, on the one side, you have a Poincare series, and on the other side, you have the sum of L functions. But once you've reached this formulation, in fact, you can see that the geometric version of it is completely symmetric. Okay, that is, the two sides are traces of Frobenius on things that are described with exactly the same words. You just swap some adjectives. All right, so I want to briefly discuss this. If you're not fluent in this language, I'm going to spend a slide or two on this, and then it won't be. Okay, wait. Let me calculate my time remaining. Okay. All right. So this is the formula. This is the line coding of this formula by an x and an x check. And what I want to briefly explain is that the two sides look completely symmetric in the geometric Langlands world. Okay, so I'm going to be brief here, but so on the left-hand side, we have this period function theta x, and I mentioned early on that it counts sections of something. It counts sections of some associated x bundle. And when you're doing, working over a finite field, when you count points of anything, you can express it as a Frobenius trace on cohomology. So if you just write that out, you're not thinking, you're just applying that blindly, you see that this theta x is the function which its values are given by, you take trace of Frobenius on the étale cohomology of a space of sections of a certain x bundle. Okay, that's the nature of it. You take the space of all sections of the x bundle, and these are coherent sections. Okay, it's something that maybe if x was a vector space, this would be a vector bundle. You're taking sections, and then you take étale cohomology of that space of sections. Now, what is less obvious is that the right-hand side has the same descriptions with, slightly informally speaking, the role of coherent and étale reversed. Okay, the x check period of rho is a Frobenius trace on the coherent cohomology of some space of étale sections. All right, so let me quickly explain that. And to avoid getting into technicalities, I'll explain it in the setting of a projective smooth curve over C rather than a finite field. So in other words, okay, first of all, to be in the setting of geometric Langlands, we should be dealing with a global field of the function field over FP, but now I'm further switching to a curve over C rather than over FP. Okay, so here's the story. Given a G-check local system and a space X-check, you can produce from that a kind of X-check local system. So, same deal. You have some transition functions and you use them to build an X-check bundle. Now, this is a flat bundle. The nearby fibers are identified, okay, because you came from a local system. So you can look at sections of the bundle. It's now natural to look at flat sections because it has nearby fibers are identified. You can look at flat sections. And what is a flat section? It's something which, as it has to have a value everywhere. And when you go around, it must come back to where you started. So this is exactly the same thing as a fixed point of the Galois representation on X check. Okay, so you see the first ingredient of the spectral period was a sum over fixed points. And those are related to sections, just as on the automorphic side, we were counting sections. But then you had the L function. And I say something about where that comes from. So this space of flat sections or the fixed points, the fixed points of this monodromy action X check, you can endow it in a natural way with the derived structure. Okay, so even if isolated classical fixed point, the natural way to define this as a derived scheme. And then this classical fixed point has a kind of some thickness in a derived direction. And if you compute that, what you find is each fixed point, the algebra of functions on this derived ring gives an exterior algebra on the cohomology of its tangent space. And that vector space categorifies the L function. When you take Frobenius trace on it, it recovers the L function. Okay, so this is kind of gives you a starting point of how to formulate these conjectures from the point of view of geometric Langlands. For the point of my talk, though, I just wanted to say that this is, maybe this doesn't buy you anything over a number field, but it's a beautiful fact that the two sides now are exactly symmetric. Okay, they can be defined with the same words. Oops, sorry.
Sorry, actually, you said this exterior algebra is the ring of functions on the derived fixed points. Is that
yes,
right?
Yes, that's right. That's right. Exactly. Yeah, like in this isolated fixed point, the derived fixed locus would just be a shifted copy of the H1, and the ring of functions gives you an exterior algebra, and then taking Frobenius trace formally gives you the L function. Okay, so now I want to move on to the next part of indexing periods by Hamiltonian spaces. Are there any questions? Well, you can ask questions anytime, but I thought I would stop and see if...
Sure, yeah, not at the moment.
Okay, all right. So this is a fairly satisfactory story. That is to say, when it is applicable, it gives you a very pretty picture of a way to think about the period. At least the way I introduced it, it depended on a certain numerical coincidence to define a reasonable candidate for this space. Okay, namely, this graded representation had to match with a quotient of Lie algebras. Now, even when that coincidence doesn't work, it sometimes works. But anyway, the bottom line is there are many periods where you don't have such a candidate for X check. But nonetheless, you find, so if you just look at examples, I won't say something precise here, but if you look at examples, you find two things often happen. And really, you should be looking at tempered examples here. The first thing is the graded representation W, it always contains that quotient of Lie algebras. Okay, it's not equal to it, but it's when I say contains, it means as a representation of check GX, it contains a copy of that quotient. It might be bigger. And the remainder is symplectic. Okay, so it has the thing I said before plus something symplectic. And so if you were, especially if you know to be looking for something symplectic, if you're kind of thinking, well, I'll try to define, even if I can't define X check, maybe I can define its cotangent bundle. This suggests kind of doubling the previous definition. Okay, so in the previous definition, this is again this contracted product. So it's check G times W quotient by check GX. So this is in the cases we were in, this sort of two copies roughly of what I said before. Okay, so this is going to be something we study, but let me give you a couple of preliminaries first. So I have given you some fairly simple examples of how this data, check GX and W, arise. Okay, and just to remind you that check GX tells you when the period is non-zero and W tells you what it is when it's non-zero. Now, in the previous examples were quite simple. One of the reasons is that you can use the Whittaker normalization. In general, you cannot access that, and a sort of more useful thing to do is to normalize by the L2 norm. Okay, so here I've just written this to explain what this W and check GX should satisfy in general. So as before, when the Galois representation doesn't factor through check GX, the period is 0. And when it does, you get a formula involving the L function. This formula looks different to the earlier one, but it's really not. It's just that you should, morally speaking, think of this, okay. This formula looks a little different from the previous one because I've normalized by the L2 norm. Okay, I think this is confusing, but all right, I'm just writing this down so you can see how to define these, this check Gx and W in the general case when you can't have access to Whittaker normalization. The whole business of normalization is a little bit annoying, and essentially there's nothing special about either the Whittaker or the L2 normalization. But the bottom line is so underlying this is perhaps some one of these line bundle ambiguities that Mignon mentioned. There's no preferred way to choose an automorphic form inside this line, so you can take the ratio of 2 periods. Okay, and so you can, it doesn't really matter which ones. We use the Whittaker and the L2 because we're happy with them, but really it doesn't matter. It's just that strictly period formulas have to involve a ratio of 2 periods to get around this. Okay, and now I return to Wansu's question. Indeed, I gave you examples where W has rank 0. Sorry, the grading on W was uninteresting. Typically, it's interesting and quite complicated. And here are examples, even I took them from the simplest case when this relative dual group check Gx has rank 1. Okay, so it's SL2 or PGL2. I just pulled 3 examples from Yanis's functorial transfer paper. And this is what W is. And in the first 2 examples, the group check Gx is SL2. Standard means the 2-dimensional representation, and the square brackets are the shifts. Yanis's paper, there are also some trivial copies of the trivial representation. And I've put them again with shifts. Now these I just computed quickly yesterday. I might have got the exponents wrong, but there's certainly something a lot like this. So the only thing you should take away from this slide is the shifts are in general complicated and irregular. And in fact, I spent a very long time staring at them early on in our project. Okay, so having made that point, let's go to, oh, okay, there's another thing I want to say. So, you know, I think historically in the theory of periods, these data have been computed on a case-by-case period. There's a specific period integral, and people would analyze it and write down, maybe not in these precise terms, but information equivalent to this subgroup and the representation W. Now, the story has become a little more uniform. So if, for example, if X is a good spherical variety satisfying some mild technical conditions that make you expect a period to be an L function, you can define check Gx and W in a general way. Okay, so this check Gx, it goes back to this beautiful observation that you can, that a spherical variety has a root system attached to it. Okay, and it was improved over time. The representation W is defined as a virtual representation. And it's computed by Yanis and Jonathan Wang in their study of local Poincaré formula. So the defect is it's only defined as a virtual representation, but hopefully the more detailed study of the local conjecture, which David will mention, will rectify this. In any case, these data, it can be defined, at least in this generality, in some uniform way. And it's reasonable to hope that this good situation will generalize a little past good spherical varieties to the class of good Hamiltonian spaces that we discuss in our paper. Okay, that doesn't exist at the moment, but it's reasonable to expect that we can have uniform definitions. Okay, so now we're ready to, again, kind of encode these 2 pieces of data by a Hamiltonian space and kind of rethink of the, reformulate the conjecture in those terms. So the basic point is that if you take this contracted product, and maybe the first thing to say about this contracted product is in our first 2 examples, this is the cotangent bundle of the space we constructed before. Okay, it's sort of twice as big. It's actually the cotangent bundle. And our basic thesis is that this always has a preferred structure of a Hamiltonian space under G-check. It just has a symplectic form and a moment map. And we think of it as it indexes the a dual period for G check, as we'll see in a moment. So, all right, this repeats what I just said. In the examples of the previous section, this space is simply the cotangent bundle. And in general, the fact that it has a symplectic structure, at least in the tempered case, it encodes two features that I already mentioned. Okay, so it encodes the fact that experimentally, this representation W always contains the quotient of the algebras, and that the remaining part of W, the quotient of it by the space, carries an invariant symplectic form. So these are experimental facts, and if they are, you can check them in. It's true in every case we know, and if you check them, then we give a way to construct an invariant symplectic structure on this check M, which is not quite obvious. Yannis mentioned it in his talk, and I'll say a little more about it. Again, so we don't have a proof of these, but it's something that it's reasonable to hope that the study of the local conjecture will give us an unconditional way of doing this. That is, of putting the Hamiltonian, the symplectic form on this check M.
So distinguish tempered and non-tempered cases?
Sorry?
So how do you tell which case is tempered and which case is?
Yeah, I'm gonna talk about this now.
Oh, sorry.
Yeah, good question. Yeah, no, I mean this check M doesn't depend on whether it's tempered or not. This was just somehow some sort of the content of it being symplectic in the simplest case comes down to these observations. Okay, now in general, the main extra thing, and this is what sort of the symplectic structure on this space is not transparent the way I've written it. And the main extra ingredient is something that Yannis and I introduced in our study of local harmonic analysis, which is an Arthur SL2. It's a morphism from SL2 to the dual group associated to a given period. And what this does, it roughly indexes how tempered the representations distinguished by this period can be. So, just to give an extreme example, okay, there's a very silly period, which is the trivial period. It means you integrate every constant form, every automorphic form against a constant function. This period distinguishes only the trivial automorphic form, which is kind of the least tempered automorphic form there is, and correspondingly, for this period, the SL2 is the principal SL2 of the dual group. So I don't want to go into the details of how we construct the symplectic structure. I will just say what the upshot is for these pairs of dual periods. Okay, so once you have the once we have this way of attaching a Hamiltonian space to a spectral period, we can switch the roles just as we did in the first part of the talk. And the way the symplectic structure is constructed, it has the following consequence, which I think is easier to appreciate than the details. The Fourier coefficient, if I look at one of these periods and I look at which, if it involves a Fourier coefficient, hold on one second. For some reason, I can't highlight this, but okay. If I look at, oh dear. Sorry, I'm having some trouble. Okay. Okay, so in such a pair of dual periods, the Fourier component of one will match with the Arthur SL2 of the other. So let me just explain this by example. So an extreme pair of dual periods is the Whittaker period and the trivial period that I just mentioned. Okay, so in that pair, the first formula would be the Whittaker period for G matches the trivial spectral period, and the trivial automorphic period for the dual group matches the Whittaker spectral period. Now, the phenomenon I've just said is that the fact that the Whittaker period involves a very non-degenerate Fourier coefficient matches with the fact that the trivial period is highly non-tempered. Let me do another example with that, the Jaeho-Shalaika thing that we already saw. The Jaeho-Shalaika period, in the case of PGL6, if I'm just writing out the integral that I wrote on that second slide, okay, it's some integral over block diagonal matrices. Okay, the only thing which is relevant to us at the moment is what the Fourier component of the period. And that Fourier component of the period is a sum of an exponential character at this x1, that just should be an x11, x11 plus x22 plus x33. On the other hand, the dual period is the period for SL6 that's attached to the homogeneous space SL6 mod SP6. So that's called the symplectic period. And this has an Arthur SL2. It's a non-tempered period. And that Arthur SL2 has a nilpotent that looks like this. So that Arthur SL2 nilpotent matches the Fourier coefficient that occurs in the Jaeho-Shalaika period. And also the other way around. Okay, there are two pieces of information. The symplectic period for SL6 does not involve a Fourier coefficient. And that matches with the fact that the Jaeho-Shalaika period is tempered, that it has no SL2. Okay. So, all right, all these things were to say how to, a little bit about this Hamiltonian space. When you don't have an X check attached to the spectral side of a period, you can still attach a Hamiltonian space that generalizes its cotangent bundle. And by analogy with the previous definition of the spectral period for a G-check space, we can define a spectral period for a Hamiltonian G-check space. Okay, so this M check, you should think of it as sort of doubling X check. And correspondingly, we define the spectral period in almost the same way. We sum over fixed points of the Galois parameter, but now we have to take the square root of the L function. Okay, and but I've been sloppy about points of evaluation of that square root. There is a GM action that permits you to keep track of that, but I won't say that here. So this generalizes this is the, just as I said, what the spectral period of a G-check space is the spectral period now of a Hamiltonian G-check space. And you see, you have a trouble in defining it because you have to choose square roots. And I think our understanding of this is not quite zero, but it's certainly not very good. And in general, this is related to the fact in the theory of automorphic forms, many periods you square the period, and we don't have an understanding of the phase of the period. So this issue is not understood. It's not just a matter of this formalism. It's not understood in the theory of automorphic forms what the phase of periods are. For example, the Gross-Prasad period, it's a formula for the square of the period. And that confusion about the phase of that is related to the confusion about the choice of signs here. Okay, so as before, I wanted to just mention what is the advantage of encoding this period by M-check. Again, if you write a period formula as an automorphic period equals a spectral period for this M-check, if you unwind that has the same content as writing it as a sum of L functions. But it's easy to see once you start looking that this M-check encodes many subtler features of the period in a very nice way. And I'll mention two of them here. The first is that the grading on W, which I mentioned gave you examples to show is quite complicated. It becomes quite transparent when you view it on M-check. Okay, the way we construct this M-check is some sort of symplectic induction, but anyway, in the way we construct the symplectic structure, there's a transparent GM action. And in fact, the way I computed the GM actions in the examples I showed you is using this point of view. The second point, and this is something which I think we're just starting to grapple with more deeply in automorphic forms, is that you would like to study you would like to understand non-tempered periods more systematically. Okay, so for example, there's people, Gan, Gross, and Prasad have recently studied the behavior of their period in the non-tempered case after a lot of study in the tempered case. And in general, we expect that the behavior of non-tempered periods will be closely related to the geometry of the moment map for M check. So whether a given Arthur SL2 is distinguished will be closely related to whether that nilpotent appears in the moment map for M check. And in this Gan, Gross, Prasad case, this is actually, they remark on this in their paper. I mean, not in the language of M check, but they point out that their criterion can be reformulated in terms of the moment map. And this should be a general phenomenon. So I'm not going to give details on this. Let me just give you one example to give you the flavor. Okay. So if you look at a homogeneous period, so just something attached to integrating an automorphic form over a subgroup, and I do a rather degenerate thing and compute the period of the trivial constant the trivial function. Okay, so I'm simply computing, in other words, the volume of the subspace I'm integrating over. Now, this is a product of zeta functions, and it's very easy to compute. But which zeta functions you get are captured very cleanly, captured very cleanly by this M check. So that is, even when M check happens to be a cotangent bundle, this answer is better expressed in terms of M check than the variety of which it's a cotangent bundle. Namely, the zeta functions you get are the invariant degrees for G check invariant functions on M check. Okay, in this context, it'll be a polynomial ring, and the invariant degrees tell you the X period of the trivial representation. So that's a simple example that I think gives you some flavor of how non-tempered periods have somehow work particularly well viewed from this point of view. Okay, now, yes.
Okay, just a quick question. So am I correct that, I mean, basically the right-hand side explains Gross's motives in the...
that's right. So this example is, that's right. That's the underlying motive. So of course we understand what both, what the left-hand side is very well. All I'm saying is that it's encoded more neatly by M check than by other invariants of the. Okay, now since I'm very short on time, I'm going to skip. I wanted to work through the following example of duality. If you dualize the theta correspondence, you come to the Gan, Gross, Prasad period. And if you dualize the Gan, Gross, Prasad period, as you expect, you come back to theta correspondence. But since let me just say those words, it's hopefully I've said enough that you may be able to figure out how that works. That's a nice example to work through. And it also illustrates why you really need Hamiltonian spaces and not just varieties. So I'll go to my conclusions. So in this talk, I kind of described, I didn't propose this duality of a reductive group G and a Hamiltonian space M, and a similar thing on the dual side. Now, I should say at this point, I described we have a recipe for this M check, but we don't know that our recipe is involutive. Okay, we don't know that in all examples, when we apply it twice, it comes back to where we started, but we don't have a proof of that. So what we actually do, what we've actually done, we have a reasonable class of Hamiltonian spaces where this duality appears to be well behaved. It's a very interesting question what the correct generality is. This is not clearly, there are many interesting examples outside this, but it's a well-behaved class. And we've analyzed fairly carefully how this duality works, both from the point of view of unramified global periods and also the corresponding local story. So I've talked about global periods in this talk. Local story will be discussed in David's talk. All right, I'm going to skip this slide because I'm short on time. I want to say what are future topics that we'd like to investigate and I think should be studied. So the first thing is this duality of G and M and G-check and M-check, it's more fundamental than the study of periods. It's a phenomenon which you can see incarnated in all aspects of the Langlands correspondence. Okay, you can see it in the global Langlands, which is what we've talked about, also in local Langlands, in geometric Langlands, and presumably it also appears, say, in p-adic Langlands. Okay, it's not really about periods. It's something more fundamental, and there a useful organizing principle are the boundary conditions that David will talk about. Okay, I've focused on periods, but it's not fundamentally something about periods. And systematically studying how this manifests itself in ramified local Langlands is particularly important because that's relevant to understanding periods with ramification. Now, probably the thing I'm most interested in is there should be a fairly large zoo of exotic examples that involve singular or stacky behavior for M and M check. And you can see my talk at Bernstein's 70th birthday for some examples of this. Like these will be related to very interesting kind of exotic periods, such as some of which represent infinite sums of L functions. Okay, so there is a certain a small number of examples of nice behavior of infinite sums of L functions, which I believe will be explained and extended in this formalism. The last topic is to study spectral quantization and its local counterpart, the issue of choosing the signs of this in the square root and the local analog. And that's something which I think will be of interest in the study of L functions in its own right, independent of this story of periods. Okay, so I've gone slightly over time, so thank you very much for listening.
Thank you very much for the wonderful talk, Akshay. So, yeah, well, I have one question by Winston Leslie. Well, are the slides available?
Yeah, just email me. I'll send it to you.
Could I ask a question?
Yes, please.
It's a mildly technical question, or maybe silly question. In this G-check, M-check, when you talk about these Hamiltonian spaces, are these M-check algebraic symplectic manifolds?
Yes, yes.
And there's always a moment map?
That's what part of what we mean in Hamiltonian. It's a G-check space equipped with an equivariant moment map.
And these then these moment maps are also algebraic?
Yes. That's part of the, it's not just part of the structure that we require. And when we construct it, it comes with that.
Oh, I see. So in your construction, you're always in a situation where you do have a moment map. I see.
Yes.
And
yes.
You're saying
it's an important piece of structure. It's necessary to, for example, make sense of the local conjecture.
Right. But somewhere along the way, didn't you also say that you get into non-algebraic Hamiltonian spaces as well?
No, this is I'm not saying this, but in my understanding, this is a story about algebraic Hamiltonian spaces.
Okay. That's fine. Thank you.
You know, they can be the interesting examples with singular spaces or stacks, but no, it's still in the world of algebra.
Mm-hmm.
I have a naive question. So, I mean, given an L function we like to study, is there some sort of way to look for, I mean, which GM would realize the function?
It's a good question. In fact, you can use this to, if you have an L function, to make a guess as to what integral represents that. Because you put this L function on the, instead of putting it on the spectral side, you put it on the automorphic side, and you run this machine, and it gives you then a candidate which you can flip, which would give you an integral that represents that. So it actually gives you a way, but that process works well in many examples where there are known integrals. And what will happen is if you try it on some, however, on some complicated large L function, it starts to run outside of this nice class of Hamiltonian spaces. So it's extremely interesting to do that. As I said, so it's very important to understand what the true limit of this duality is. Because if it were, which I don't think it is sensible for all Hamiltonians, but to the extent it were, you could literally do that. You could take any L function, put it on the automorphic side, compute something, and that would give you, flipping it, an integral to represent the L function.
Maybe this is, sorry, this is maybe a related question, or but much more stupid, I think. Is there a formula, is there something like a M track if you just start from a Galois representation?
I think you have to give me a bit more there.
Right. I mean, your Galois representation, in a sense, you're always starting from an automorphic thing, right? And the L function is the L function of a Galois representation associated to the automorphic form, right? In your formulas.
Right.
But is it possible to start with just a motivic Galois representation that you don't know a priori is automorphic, right?
Well, I think the point of view I was advocating with the spectral period is that it's something that attaches a number to a Galois representation in the specific sum of fixed points way. So that makes sense without it being automorphic. But the interest of that definition that I'm aware of comes from the fact that it dualizes to something meaningful automorphically.
I see.
But it may be that the spectral period is a natural thing in its own right for some arithmetic reason, but I don't know. But by itself, it's a concept that exists in the Galois representation.
Yeah, no, I see that, but it's just that by itself, it doesn't look terribly useful, I guess, is what I was thinking.
The spectral period?
Right. I mean,
yeah, I mean, right. The thing which may be interesting about it is at these polar points where it's something a little more subtle. And I think it captures something that's not so easy to, the points where the fixed point set is not discrete. It will be interesting to study because it gives you some understanding of how you should be thinking about the poles. But you're certainly right that I don't know if intrinsically in the world of Galois representations why. Well, okay, I had something interesting to say. So I'm going to give a talk in the London number theory seminar in a couple of weeks where maybe I'll say something of interest purely about on the Galois side.
Okay, thanks.
Okay, here's another question from Winston Leslie. Can this formalism include periods not expected to relate to L functions, like orthogonal periods?
Yes, absolutely. I think that's the interesting place to go, and we have some fairly simple examples where where that works. Right, it would be very, very interesting to know the dual of GLN mod ON. I think we have, for n equals 2, it's there's a reasonable guess, and I think we believe there will be something with some mild stack, some mild orbifold points that will dualize to it, but we're not sure what it is. But yes, I absolutely expect it to include things that are not L functions, and that's the interesting direction to go.
So yeah, here's, well, I guess Jace wrote a response to Minhyung's question. I don't know if, maybe I'll just read it.
Sure.
Yeah, if you give a representation of the L group, then you can construct a spherical variety conjecturally encoding the L function.
Yeah, that is the sort of answer I was expecting.
Oh, sorry, maybe I misunderstood your question then. Okay, yeah. Anyway.
No, that's okay. Yeah, thanks.
But it will not necessarily be spherical. That's the problem.
Mm-hmm.
And I'm wondering also whether this duality interacts well with the Langlands functoriality. Sometimes we know that periods, like non-conventional periods, have to do with instances of functoriality.
This duality incorporates that, right? So the this business of the period being non-vanishing is distinguished by check GX.
Right.
Yeah. So the point is, in a way, that the functoriality and the L function fit together to give you the dual period. But yeah, so it's embedded in this already.
Mm-hmm. But it's not like you want to move, like when you have like L morphism from G check to another like H check, then you want to compare the two pictures.
No, I mean, so something which is interesting, like in this, from this point of view, sometimes you have explicit kernels of functoriality from G to H, and you know, it'll be from the way that would fit into this discussion is you could try to write down those as a Hamiltonian space for G times H and dualize them. But I would say, yeah, that's probably how the two interact. Like the theta correspondence is such an example.
Okay, thank you. I don't think there are more questions on YouTube. So if there are no more questions, let's thank Akshay again for this wonderful talk.
Thank you, Sabur.
And we'll resume in 4 minutes.
Okay, I'm going to run back to my house, so I will log in from there.
Thank you very much for beautiful talk.
Thank you. Yeah, that was great.
Yeah, it's wonderful.
I'll see you in a...
Actually, there was a last comment by Jace. If there is anything to do with the Brugman-Kasdan theory.
I haven't thought about this. Perhaps Yanis has, but I haven't.
Okay, thanks.
Hey, welcome back. The second speaker today is David Ben-Zvi, professor of mathematics at the University of Texas at Austin, where he has been faculty since 2003. He obtained his PhD from Harvard University in 1999 under the supervision of Edward Frankel, after which he served as L.A. Dixon instructor at the University of Chicago. He was elected a fellow of the American Math Society in 2012, and he was a Simons Fellow in 2017. His current interests lie at the interface of geometric representation theory, derived algebraic geometry, and topological field theory, and specifically in exploring and utilizing the perspective on representation theory and the Langlands program provided by the physics of supersymmetric gauge theory. The title of his talk is Geometric Langlands Duality for Hamiltonian Spaces. Please welcome Professor Ben-Zvi. The stage is yours.
Thanks so much. Thank you so much for the invitation. It's a great honor to be here and to join this beautiful conference. So let's see, let me share something with you. Okay, great. So this is my talk, a relative Langlands duality in Hamiltonian spaces. So I will continue the series of talks of Yannis and Akshay. So everything I will discuss is joint work. And what I'd like to address in this talk, I'd like to explain how we're going to try to extract these spectral periods that appeared in Akshay's talk, these Hamiltonian G-dual spaces, out of the kind of things that Yannis explained, Hamiltonian G varieties. So what is the automorphic periods? So what is the process of starting with an automorphic period, and how do you see from that the spectral period? And the way I'd like to explain that is through part of a kind of a bigger package, which is a package for how to encode a lot of things in the Langlands program, which I find very appealing, which is the perspective coming from topological quantum field theory. So this perspective on the Langlands program comes out of the work of Kapustin-Witten in the geometric Langlands program. Kapustin-Witten explained how to see the structures of the geometric Langlands program in a very natural way out of electric-magnetic duality in four-dimensional gauge theory. What we'd like to do is to kind of add a layer to this, an important layer in the physics, which is the study of boundary conditions. This was studied by Gallardo and Witten in the physics context. I should mention, Gallardo and Witten studied a duality for boundary conditions. And we'd like to apply this in this arithmetic analogy. So we're going to see the dual spectral period arising from this perspective as some kind of moduli space attached to the automorphic period when we think about it as a boundary condition. So I'm going to assume that this is an audience that hasn't been exposed to a lot of physics outside of Mignon's beautiful talk yesterday. So I'm going to kind of give you the kind of rough structure of what a topological field theory is without assuming a lot of exposure to this, and say how it applies to structures in the setting mostly of function fields in finite characteristic. Okay, so let me start with a kind of bit of a review about topological field theory. And again, we've seen some of these pictures in Mignon's talk yesterday. So here's the kind of classical Atiyah-Siegel setup for topological field theory. So I'm going to fix a tensor category. So I'm calling C my tensor category. So it has a unit and it has a tensor product. It's a symmetric monoidal category. It's a commutative tensor product. And at the bottom of my slides, oh, okay, I guess there's some footnote missing, but okay. So there's a symmetric monoidal category, and it'll be useful for my notation to have a separate notation I'll call C bar for what I get by taking the endomorphisms of the unit of this. So just to make that concrete, I'm going to typically, if you look at Atiyah and Siegel, you take C, this category, to be just a category of complex vector spaces with usual tensor product. And the unit is the one-dimensional complex vector space, and its endomorphisms are the complex numbers. So we have kind of two tiers in this structure. There's a tier here where we have something in C, and a tier where we'll have something in C bar. So a vector space and a number. Okay, so what is a two-dimensional topological field theory? And please, this is, I guess, material that maybe is not very familiar to people with a number theoretic background. Please ask lots of questions and interrupt. Okay, so what is a two-dimensional topological field theory? We're going to think of it as a functor, given again by the picture that Mignon explained. It's a functor from something I'm calling board 2, the category, Boardism category 2C. It's a tensor functor. So what is board 2? So objects of board 2 are unions of circles. So one-dimensional oriented manifolds And the morphisms are going to be bordisms, oriented bordisms. I think of this as a morphism from 3 circles to 2 circles. So that's the idea of the category. And composition is composition of bordisms. So I can stick another bordism at the end of this one. In fact, composition will play almost no role in this talk today, so we can ignore that. What is the monoidal structure? I said it's a tensor functor, so it's supposed to take disjoint union of manifolds to tensor product of vector spaces. So we're supposed to attach to the circle of vector space, a disjoint union of circles just gets tensor copies of that vector space. And then there's an extra structure, which we don't really feel so much in the usual geocegal setting. We're going to require or give a structure that this field theory is locally constant when I vary my manifolds. When I look at paths of manifold, everything is locally constant in that manifold. That's kind of a technical feature. So here, this picture of this bordism encodes a map. I have the vector space attached to this circle, tensor the vector space attached to this circle. This picture encodes a map to this vector space. Okay. Great. So what kind of things do you get out of a TFT? So I don't want to think a lot about the axioms. I want to think of what are the kind of characteristic features. What are the things you're going to see when you look at a TFT? And these are going to be things that we're going to translate to a finite field situation. So the main thing we might notice is that if I have a closed surface, I can think about this as a bordism from the empty set to the empty set, and I get a map from the one-dimensional vector space to one-dimensional vector space, so I get a number, or in general, that's what I'm calling my C bar. I get an invariant, which is a number attached to a closed surface. Okay. So that's the kind of first thing people like to see. You get invariants of closed manifolds. The next thing you'd like to see is, well, if you have a circle, that's my one manifold, I have the functor attaches it to it something in C, that's my vector space. And if you look at some of the pictures with like elbows, you can convince yourself that this vector space is, the analog of the physicist's Hilbert space. This vector space is canonically isomorphic to its dual. It's going to be a self-dual vector space. So I'm going to use a lot of duality without talking about it a lot. I'll reverse a lot of arrows using duality just to change the way I want to think about things. So, okay, so we have numbers attached to closed surfaces, or elements of this C bar, and vector spaces, or objects of the C, attached to the circle. Now, one of the main things of interest is what are called correlation functions. So if I give you a finite subset of a surface, so I'm going to think about this finite subset, I can think about it in 2 ways. I can think about it as, so I take my finite subset and I'm going to remove it, and then I remove some disks around it. And so I can think about pictures like this, where I have a surface minus a bunch of disks. And I think about these as I have a bunch of incoming disks and nothing outgoing. So I have here 3 circles, and here I have an empty set. So this defines a functional from a map from the tensor product of the vector spaces attached to the incoming circles to the unit, to the complex numbers in our example. So if I think of all the circles on one side, I can think of this as giving a functional. Or if you prefer to think dually, I can reverse all these circles, reverse this picture, and I think of the same picture as defining a bordism from the empty set to 3 circles. And so that gives a map from the unit to this tensor product, so an element of this vector space. Okay. So if I have a punctured surface, you can decide to think of it either a functional on a bunch of copies of your vector space or an element dually. Okay. So what does that mean concretely? This is what a physicist would call correlation functions. If I give you a vector in the vector space attached to each component, I get a number. So I get a function depending on my location of points and which vectors I put at each of these inputs, I get a number out of them. So these are our correlation functions. Okay. So this is kind of a rough schematic of, this is kind of one of the first main structures I see out of a field theory. Have I lost anyone so far? Is this okay? Okay, so that's the first structure. I'm going to be thinking about pictures like this. Let me give an example to make this a little more concrete. This example is not really going to be so relevant later, but just to orient this. So suppose you start with a finite group. You can write down a very nice topological field theory where I'm going to attach to a closed surface. I'm going to attach a number. So here I'm in the setting where I'm really attaching numbers to closed surfaces. And I just count the number of representations of pi1 into gamma. Count them with multiplicity given by automorphisms. So it's just a count of the number of local systems, or gamma covers, if you want, of sigma. That's the number. Now, what about the circle? To the circle, well, I'm going to take the same kind of construction, local systems, but I'm evaluating it on the circle. So I look at local systems on the circle. These are just elements of gamma up to conjugacy. So just get the monodromy of a gamma cover on the circle. And I can look at functions on this that are invariant on conjugation. In other words, just class functions on the group. So the vector space I'll attach is the vector space of class functions. And the number to a closed surface is the number of local systems. And then these kind of invariants, what are these kind of invariants that I'm referring to? Well, you fix your favorite class functions on each incoming circle. So for example, you can fix a conjugacy class on each coming circle, and you can count the number of local systems with given ramification data. So look at local systems with given monodromy around each of these punctures. So that's another number. So that's what these numbers I'm attaching to. So if I have a surface with some marked points, I'm giving a number every time I give you data at each of these points. Okay. So that's how to think about these correlation functions things. Okay. Now, here's another crucial bit of structure that I have. The crucial bit of structure is what's called operator product. So I have this vector space, I don't know, I called it here H. I have this vector space Z of S1, or the object I attach to the circle. And the vector space I attach to the circle has a multiplication. And you can see that multiplication in several ways. The way it's usually drawn in physics is the pair of pans picture. I have this kind of pair of pans as a bordism from two circles to one circle. And so that defines a map from Z of S1 tensor squared to Z of S1. That's my product. So for example, in our previous example, for class functions, this is the usual multiplication, the commutative ring structure on class functions on a finite group. Another way to draw the same picture is kind of flatten it, to draw it as a picture in the plane. This is how homotopy theorists like to think about this. They call it the little disks picture. And again, this is the same picture, just flattened. So I have two incoming circles and one outgoing circle. It's called the little disks multiplication. Or the way it originally comes out in physics is what's called operator product expansion. Is I really think of having one operator sitting at one point. Operator, I just mean an element of my vector space. I have one operator sitting here, one operator sitting here, and I think of those 2 points colliding. So what does colliding really mean? In topology, it doesn't mean much. It just means I have 2 points and I encode them, I enclose them in a bigger circle. And so that means kind of I look far away, instead of having two operators, I just have one. That's the operator multiplication. So you have a multiplication on this vector space with this object attached to the circle. That's called the operator product. And it looks commutative because you can move these points around each other locally constantly. Okay, so well, maybe I'll return to the commutativity in a little bit, but let me just point out that even just with these structures, you can notice something that might remind people of adelic constructions. Actually, I remember a talk when I was in grad school. There was a talk by Jean-Luc Berlinski where he wrote down the formula C of t equals CFT. That class field theory and conformal field theory have extremely similar structures. And this is somehow one of the things Witten and Valence and Drinfeld and other people noticed in the 80s. So just to say that these kind of correlation functions, I can make an adelic version of them. I don't need to remove finitely many points. I can remove any subset of points, or if you'd like, I'm thinking of removing the little disks around each of these points, as long as I put the unit at all but finitely many. Oh, I should have said that this commutative ring has a unit. There's this bordism, so the disk is something with boundary of the circle. This defines an element in the vector space or the object attached to the circle, and that has a nice feature of being a unit. If I draw a pair of pants and I fill in one of the disks, then I just get a cylinder, which is the top TFT version of doing nothing. Okay, so there's a kind of an adelic construction here, and you have a kind of a restricted tensor product. You can make your object at any collection of points. At all but finitely many points, you put the unit. And moreover, as the points collide, there's some kind of fusion that happens. If 2 points are very close, you can enclose them in a bigger disk and multiply them, and you get the same answer. So this is mathematically encoded in something called factorization homology, which won't be necessary for the rest of this talk. Actually, this slide is maybe just ignore it. But here's something that is important. what is important is that there's a commutativity for this multiplication. So when you multiply, so I'm, if you've probably noticed that I'm being kind of very vague about, or very flexible maybe, about the values of my field theory, whether I'm attaching vector spaces or objects in some more general categories C. And the more rich your target categories, the more phenomena you start to see. So this is something you don't see in the setting of just vector spaces. But when you start looking a little more at the commutativity, you discover that it's commutative only, this multiplication is commutative only in a homotopical sense. It's commutative up to homotopy. What does that mean? If I have, here's in my picture, I have two circles, there's a path where I can rotate them around each other. And so I get kind of a homotopy between a product one way and a product going the other way. I can take these two things, and I've said everything should be locally constant as I move my points around. I come around to where they have switched position, should get the same multiplication. But if you look at this picture, and I tried to draw it the way that everyone learns in undergrad topology or graduate topology, why pi2 of a space is commutative. When you learn why the second homotopy group of a space is commutative, you draw pictures like this, that elements of pi2, you can kind of shrink them and move them around each other. And pictures like this are why pi2 is commutative. And so the kind of commutativity is the same kind of commutativity that appears in pi2. In homotopy theory, this is called a braided or an E2 algebra, an algebra over little two disks. So there's some subtle, there's a commutativity, but there's some kind of lack of commutativity also. And that's going to be very important for us. We're going to try to measure the fact that this multiplication has some extra structure. And the nicest way to encode that is to say it's something like a Poisson bracket. So in addition to this operation of multiplication, there's another operation, which is a bracket, which measures the lack of commutativity here. So I don't want to define it very precisely here. There's a couple of ways of describing it. One way of describing it is it's really coming, you look at the space of pairs of points in the disk, and there's a homology class here, which comes from moving one point all the way around the other one. This defines some kind of homological operation, which is playing the role of the Poisson bracket. So that's one kind of thing you could do, or if you like braided tensor categories that Min-Young mentioned, this is exactly the braiding operation. Another way to say it, if you like, one way to think about Poisson brackets are things that you quantize. A commutative ring with a Poisson bracket is a hint that there should be a deformation, which is a non-commutative algebra. Like the first order data of non-commutative deformation. And one way to do that is you take your object attached to the circle and you work equivariantly for rotation of the disk. Here's my circle, and I think work equivariantly with respect to rotations, I end up getting a one parameter deformation, which breaks commutativity. So I don't want to get very technical in this, but I just wanted to emphasize that you get a commutative multiplication and you get something extra. And this is fundamentally going to be why Poisson structures or Hamiltonian spaces appeared in the previous talk from this point of view. That there's some residue of non-commutativity that you can see in these products when points move around on a curve. Okay, did that make some sense? All right, so I won't go into this in detail. I'm just going to assume that there's some way to measure something more than a commutative multiplication, and that'll give us a Poisson structure. Okay, so that was the crash course on topological field theory. And those pictures are basically all the pictures we're going to need. One more I'll add. So now I'd like to explain a point of view on the Langlands program from topological field theory. And this is very much in the spirit of Min-Young's talks and thinking about Min-Young's arithmetic transassignments theory. I want to think of a kind of field theory that I can do in an arithmetic setting, and will have the same kind of structural features. So the dictionary I want to do is I'm going to replace my topological surfaces by curve over finite field. So I'm not going to try to work over number fields, but let's kind of have this happy middle ground. Let's work over finite fields. So instead of a topological surface, I'm going to draw all the same kind of pictures, but for curves over finite fields. So I need to tell you how to translate the pictures we saw in the previous slides into pictures that make sense in algebraic geometry. And so what do you need to know? Well, okay, again, I'm going to draw a curve over a finite field, the same thing I draw a topological surface. That's my curve. So that's my C now. I changed from sigma to C. And now instead of having circles and disks, which were some of the main ingredients in what we had before, well, we have disks and puncture disks in algebraic geometry. We can take the local ring around a point of the curve, and we can take the local field around that point of the curve and take their spectra and we have a version of a disk, and inside of it, a version of the punctured disk. So the punctured disk is going to play a role of the circle. The disk is going to play a role of the disk. Okay. All right. So that gives me at least the basic ingredients that we had before. And there's a beautiful theory, the attempt is of what people call algebraic field theory on curves. That's the title of a beautiful manuscript of Beilinson, Fagan, and Mazur. And again, this is ideas that Witten and then Beilinson and Drinfeld developed, that you can see a lot of algebraic field theories, algebraic structures from field theory appearing for curves over finite fields. So the basic idea is, again, we're going to attach invariance to curves and disks and punctured curves the way we said before. One thing I'm going to suppress is the analog of functoriality in the field theory, the analog of Bordisms. You can formulate that. It involves nodal degenerations of curves. You have to describe what happens when your curve undergoes a semi-stable degeneration. That's not going to be relevant at all for today's talk. Okay, so that's the setting we're going to work with. We're going to have some kind of analog of field theory living on curves over a finite field. Now, I can't draw a pair of pants, but I can draw pictures like this. I can have pair of points that are close to each other. And Beilinson and Drinfeld formulated very beautifully what becomes of this pair of pants multiplication in this algebraic setting in the theory they called the theory of factorization algebras. So factorization algebra is not literally an algebra in the usual sense. We're not just going to have a vector space with a multiplication on it. We don't have this Bordism pair of pants. What we're going to have is kind of a process. So factorization algebra is a kind of algebra where it's kind of a process. You have 2 points in a curve, and you let them collide. When the points are distinct, you might have 2 copies of a vector space. When the points are colliding, you have just 1 copy of that vector space. It's some interpolation between 2 copies of something and 1 copy. That's this merger. That's the theory of factorization algebras introduced by Beilinson and Drinfeld. So again, I don't want to define it precisely, just to say that there is a way of defining this multiplication in the algebraic setting. Okay. All right, so should we, so now I'd like to give an example of the structure that will be very familiar to people, maybe not in this language, which is the Langlands program. And right now this talk, I'm going to spend almost all the time on the automorphic side. If there are questions at the end, I can spend more time on the spectral side. I'd like to explain some of the structures on the automorphic side of the Langlands program, and then a little bit of the duality. So I want to think about the theory of automorphic forms over a curve, over a finite field. It fits into this algebraic field theory. I'm not going to give it a different name. I'm just going to say TFT. There's a rigorous mathematical structure you can formulate there that has an analog of topological field theory, but I'll just draw the pictures that I'm going to need. So there's a topological field theory I'm going to call AG, the automorphic theory attached to a reductive group G. It's not going to have the same kind of values as in the T.S. Siegel. To a closed surface, we're going to have a vector space rather than a number. And to a punctured disk, we're going to have, rather than a vector space, we're going to have a category, a k-linear category. K is going to be our field of coefficients. I'll think of it as a characteristic zero field. Okay, so how does this relate to Langlands program, to automorphic forms? So to a closed surface, what do I mean by closed surface? I just mean projective curve. To a projective curve, I need to attach a vector space. And that vector space is going to be the vector space of unramified automorphic forms on this curve. So we look at functions on the space of G bundles on this curve, F2 points of bund G of C. So this is basic vector space for unramified automorphic forms. So that's the kind of setting. To a closed curve, we're going to attach a vector space. What about the local picture? The local Langlands picture is now we have this field F. I should point out that my field F is always going to be the local field. I don't have a notation for the global field. So F is going to be a field of Laurent series. So the local picture, I need to give you a category attached to a circle. My version of circle is a punctured disk, or the field F. So to F, I'll attach a category, namely the object in local Langlands, the category of smooth representations of the group G. Okay. So I'll take the loop group G over F. I guess I put an X here. I take the group G of F, and I can attach the category of smooth representations. There's kind of a footnote here that there's a slightly better, in some sense, bigger space having to do with isocrystals, but let's forget about that. So in usual local Langlands, we think of the category smooth representations of G over local field. So we have a vector space attached to a curve and a category attached to a local field. And what are some of the relations? So for example, inside of this category, so that's my analog of the circle, I should have an object attached to a disk. That was the analog of my unit before. So inside of this category, I have this basic unramified representation. I look at functions on G of F, not G of O. Okay. So that's a basic object in here. And moreover, I have the ramified Langlands program. So before I had the unramified vector space, but the vector spaces of ramified automorphic forms fit in like this way. I have a curve. I have finally many points. I specify ramification data at all these points, and then I get a vector space. So that's exactly the kind of structure we had before. I have data on each circle, then we get a vector space out of that. And that's a vector space on automorphic form with given ramification data. Or if you want to think dually, you can think of the space with full level structure on this finite set S, and think of that as a representation of this group over the local field. So
sorry, David.
Yes.
I guess you explained this before, but I should think of this as a 4-dimensional theory somehow?
Yeah, I'll get to that. And let me return to that in a couple of slides. I mean, this is really, I'm really thinking about these as being 3 manifolds. The curve is being a 3 manifold. So there's a secret circle here.
Yeah.
So I'm attaching so it is, I'm thinking about 4-dimensional field theory. I'm attaching a vector space to a 3 manifold, which is a 3 manifold fibered over the circle, my curve over a finite field.
But that vector space is infinite dimensional now, right?
That's right. So let me, maybe this is an interesting comment. When I say 4-dimensional, what do we mean when we say dimension of a topological field theory? In physics, most things that a physicist would talk about as being 4-dimensional field theories are not what a mathematician would, what a T. N. Siegel would recognize, because they essentially never have well-defined numbers for 4 manifolds. So when we talk about 4-dimensional field theory, that's kind of giving the idea we'd like to attach numbers to 4 manifolds. That involves analysis, as it appeared in your talk. That's not going to make sense in algebraic formalism, and maybe not make sense at all. A 4-dimensional TFT for me is something that attaches a vector space to a 3 manifold. And this is the typical of all gauge theories. Gauge theories don't tend to give well-defined numbers on 4 manifolds without a lot of fiddling around. So maybe that, I don't know if that helps the numerology here. So I'll get back to this numerology of 4 in a couple of slides. Okay. Does that answer your, or locally answer your question?
Totally, yeah. Can.
Okay, so let me now focus on another aspect of topological field theory that I suppressed before. This is one of the most interesting aspects of the structure, and also appeared in Mignac's talk, which are the notion of the operators. So there's, in topological field theory, there's all kinds of defect operators of various dimensions, all kinds of singularities of your field that you can allow. And what I'd like to focus on today are what are called line operators or 't Hooft line operators. Numerology of where line comes from, that's really you should think maybe these are codimension 3 defects, but in any case, we're going to talk about line operators, or specifically what in physics are going to be 't Hooft line operators. But this is something general I can formulate in my field theory formalism. So what is this? I'm going to attach an object, which is, I take endomorphisms. So I have something attached to the circle. Inside of it, I have something distinguished attached to the disk. So I have this kind of unit, this object attached to the disk inside of the circle. And I can think of endomorphisms. So the way endomorphisms are kind of seen pictorially is I think of gluing 2 copies of the disk to itself, and I get a little sphere, or maybe it's better to draw it not as a sphere, as a kind of raviolo or bubble, or flying saucer. I guess flying saucer would be kind of this picture. So I'm thinking of kind of taking 2 disks and gluing them together away from one point. This kind of non-Hausdorff picture. So, but in any case, here's a well-defined mathematical formula. I can take endomorphisms of this, what I attach to the disk inside of what I attach to the circle. And these are Hecke operators in the Langlands program. So you might say, I use the word codimension 3, and you might say, where does 3 come in? All my pictures have been 2-dimensional. So how do you think of Hecke correspondences? You can think about, you take bundles on a curve, And you can have, there's a natural correspondence between pairs of bundles on the curve where you identify them away from one point. So the Hecke correspondence means you look at bundles. You can think about it as bundles on the ravioli. Two bundles that are identified away from one point, and you can remember either the left one or the right one. This is a picture for the Hecke correspondence. The beautiful thing I learned from Kapus and Witten, in the way to draw this in physics is, if you like, you just add another variable, which is time. That's where the three-dimensional picture is. You think about this rather than being a static, this correspondence, this Hecke correspondence is a static thing. You think about that as being this secret time variable. That's my extra dimension. And as some process that I start from one bundle on a curve, I end up with another bundle, but in the middle, some singularity as a curve. That's a 't Hooft monopole. It's something of codimension 3 in this picture. Okay. So again, I don't necessarily expect the physics intuition to make sense, but at least I want to say there's a well-defined mathematical object I can attach here. And this object has associative product. Well, because I wrote it as endomorphisms of something. I wrote it as something attached to the disk inside of something attached to the circle. So it has an algebra structure by construction, but it also has something else. So here I tried to illustrate this process. My two bumps, my green bump and my, I don't know, red bump, brown bump, I'm not sure. There's supposed to be two of these Hecke correspondences that I'm trying to compose. So the normal composition is do one and then the other. But I can also just imagine sliding one off the other and moving them around on the curve. So there's kind of two directions, if you'd like. There's the honest composition of these operators, and then there's this factorization picture. I can move the points where I do modifications around on the curve. Okay, so there's factorization plus composition, both happening at the same time and in a compatible way. So that kind of explains the commutativity of these line operators. They have kind of two different kind of axes, really three axes. There's kind of a vertical axis and then the kind of two directions along the curve. Okay, so that's the algebra of line operators. Okay, now let me tie it into something familiar. This is some physicsy picture, but it's supposed to explain something very well known in the number theory. Namely, this is going to be the spherical Hecke algebra. So in our situation, if you write down the formula, what I wrote for this H, it's endomorphisms of the representation, which is functions on G of, it's not called K anymore. You look at functions on G of F mod G of O as a G representation, and that's the spherical Hecke algebra. So that's exactly the object I'm attaching. So this little bubble algebra is the spherical Hecke algebra. And what do we know? The spherical Hecke algebra is commutative. So that's usually explained using the Gelfand trick or something like that. This is somehow a deeper explanation for the commutativity of the spherical Hecke algebra. It comes from geometry. So this is Beilinson and Drinfeld's explanation. It comes from the fact that we don't just have ordinary composition or the Hecke structure, multiplication of double cosets. We also have room to move around. We can move the points around. Okay, so the spherical Hecke algebra, that's our bubble operator. These are the line operators in our field theory. So it's something intrinsic to the structure of field theory. And so it's our commutativity. So in particular, we also see that unramified representations have a tensor product. They're modules over a commutative ring. So we're seeing some of the commutativity in, again, that's part of the field theory. Now, one of the key features is that it's a Satake isomorphism, telling me that this spherical Hecke algebra has a Langlands dual interpretation. It's isomorphic to the representation ring of the dual. That's the Satake isomorphism. So it looks like class functions on the dual group. So that's a Langlands duality statement for these bubble operators. And that statement extends to a duality for this entire field theory. So you can express the Langlands correspondence as an equivalence of two field theories. So I explained the automorphic side as a field theory. You can similarly do the spectral side as a field theory. I'm not going to spend as much time on this. I want to emphasize automorphic side, but you can organize the spectral side in a completely analogous way. This appeared to some extent in Akshay's talk. On the dual side, we're studying spaces of Langlands parameters. In other words, G-check local systems on my curve. And I'm going to do algebraic geometry on those spaces. That's what the dual side. So for example, to a closed curve, I'll attach a vector space, which is something like volume forms or functions on the space of local systems on the curve. to a punctured disk, so in the local Langlands situation, I'll attach the category of coherent sheaves on Langlands parameters. And kind of a strong form of the local Langlands correspondence is an equivalence between this category and the category of smooth representations, or some variant, and this space with the space of automorphic forms. So and all of the structure in the two sides, all the structure field theory is matched by the Langlands correspondence. So this is a nice way to encoding the structure in the Langlands correspondence. And the key thing that makes the Langlands correspondence work, the key compatibility, is we want to match these line operators. On the automorphic side, we have these 't Hooft operators, the action of spherical Hecke algebra at all unramified points. So again, I should draw my picture. I have my curve, and I have some points. Maybe there's some points with ramification, but at every point where I don't have ramification, I can imagine gluing in one of these bubbles and modifying and this gives you operators that act at all unramified points. So this guys act at all unramified points. On the spectral side, you can write down this corresponding line operators, and you find the representation ring of the dual group. So on both sides, these basic operators are labeled by representation of dual group. They're related by the Satake correspondence. And that's what makes the Langlands correspondence tick. At all unramified places, we have to make identification between action of spherical Hecke operators and the trace functions of Frobenius. Okay, so that was the Langlands correspondence in a nutshell for function fields in this language. Okay, so I'm going to now go to geometric Langlands, if that's okay. So now let me explain, this is closer to what Kapus and Witten were actually studying. They were studying the geometric Langlands correspondence over complex numbers. I'm going to stick to the finite field setting. But the geometric Langlands correspondence, so the geometric Langlands correspondence, you can think about as living, instead of over a curve over a finite field, I look over the algebraic closure. So I like to call C bar the curve over the algebraic closure. And now we have another topological field theory. I denoted just now, it's a calligraphic A. The confusion is intentional. I want them to look very similar. There's now another topological field theory, but now it's categorified again. So before, in the beginning, you might have tried to attach numbers to curves, but in the Langlands program, you attach vector spaces to curves. Now we'll attach categories to curves. So to curve, we attach the category of unramified automorphic sheaves. So you look at sheaves on the stack of G bundles on this curve. Technically speaking, you should impose some nilpotent singular support conditions. There's so modified what exactly you mean by sheaves. But let's just ignore that. There's a category of sheaves on the stack of G bundles on the curve. That's the global thing. In local geometric Langlands, I don't want to get too deep into higher categories, but in local geometric Langlands, to a local field, you attach a 2 category. This is the 2 category of all categories with an action of the loop group. So you have this group G over the local field, and you look at representations of that, now not on vector spaces, but on categories. Okay, that's some beast you can attach. That's what we're attaching to the circle. And to the disk, there's a particular object in there, this unramified object, which is sheaves on the affine Grassmannian, sheaves on the quotient of G of F by G of O. So that's a particular category with an action of the loop group, sheaves on the Grassmannian. And more generally, you can formulate the local theory, local geometric theory, the ramified geometric theory. You specify a bunch of points on your curve, and you allow ramification at those points. The ramification data are given by this local category. And so you look at categories of sheaves on bundles with some ramification data. Okay. So none of the details of this are going to be crucial to what I want. In fact, everything I'm going to say for the rest of the talk is really about the unramified situation. So you can ignore ramification, ignore local Langlands for most of what we're going to say.
Excuse me, David, just to make sure, you're thinking that you still have the same field theory, right?
Yeah, let me skip to the next slide. Yeah, so that's the picture. So this is, so Mignon's question is the key one. So the idea is that these are not 2 different stories. You can formulate them not knowing about each other. But really there's a single beast, which is what I'm calling a 4-dimensional field, arithmetic field theory. And again, with a caveat that 4-dimensional doesn't mean there are going to be interesting 4 manifolds around. We have 3 manifolds, as in Mignon's talk. 3 manifolds will be things like curves over finite fields or rings of integers over number fields. So we're not going to actually get a lot of interesting form manifolds. But the idea is that these two different A's are the parts in dimensions 1, 2, and 2 and 3 of the same field theory. So you can, there's a single structure, some arithmetic version of a 4-dimensional field theory that encodes both this geometric and classical Langlands. And a lot of this can be made much more precise now, thanks to the work of these Rinken, Gates, Gorey, Kazhdan, Raskin, Rosenblum, Warshawski, or AGKRRV. And they explain that, at least on the unramified story, that you can recover the unramified Langlands story, unramified automorphic forms, by taking a trace of Frobenius on the geometric story. So there's a precise relation. And you know, in point of view of topological field theory, taking trace of Frobenius means roughly taking product with a circle, or really taking mapping cylinder of Frobenius. So now we've replaced a 2-manifold by a 3-manifold fibered over the circle. So if this is the picture for C bar, and the whole thing is a picture for C. So it's really both are parts of one richer story. So you don't need to think about them separately. And that's going to be useful for our project, because we want to think about ways things like periods will appear in all different parts of this theory. There are many kind of corners of this theory, and there's a beautiful single beast. Okay, so in some sense, Langlands and geometric Langlands are not two separate stories. It's one thing.
And I guess what you're saying is this is a theorem now, right? No.
There's a theorem about the unramified space of automorphic forms being the trace of Frobenius. So there's not a statement, I'm making much stronger statements about field theories that are not theorems yet. So they're writing so many papers that they weren't at theorems yesterday. But there is a theorem that tells us that the space of automorphic forms is the trace of Frobenius on the appropriate category of sheaves on bun-G.
Right. So
that makes us into math rather than dreams. But again, none of that's going to be important. For me, what's important is that this perspective in field theory encodes both arithmetic and the classical Langlands over function fields with the same kind of machine, same structure. Okay, and this 4 is where Kapus and Witten are working. This when we're studying 4-dimensional gauge theory. That's this 4. Okay, but let me get towards where we want to go. So we talked about these line operators, these bubbles. So that was one of the key features in a field theory. So whenever we had this field theory, we could look at this endomorphisms of what you attach to a disk. So that's what I was calling this bubble or ravioli, UFO. Now, line operators. So in geometric Langlands, you just work through the definitions. I gave you enough to reconstruct this. What you get, the bubbles give you equivariant sheaves on the affine Grassmannian, which is called the spherical Hecke category. So just like before we got the spherical Hecke algebra, now we get the spherical Hecke category. And the bubble picture tells us that this category has an associative convolution. Well, all Hecke things have associative multiplication, but it also has this factorization structure we should think of as being mostly commutative, or Poisson, having some commutative aspect, but maybe some non-commutative aspect. I'll make that more precise in a second. The famous, the more familiar story is if you look at the abelian category. So I have kind of slipped under the rock that when I say sheaves, everything is going to be derived. Everything I really am talking about is everything is derived. But if you just look at the abelian category, the heart of this spherical Hecke category, in other words, perverse sheaves on the affine Grassmannian, the convolution is literally commutative. And again, to actually see that, it's not so easy from classical number theory, why our spherical Hecke algebra is commutative, but Behrens and Drinfeld exactly use this factorization picture to see it's commutative, to give the commutativity constraint. So this PFT picture is really where this comes from. And the geometric Satake correspondence of Lustig, Ginsburg, Drinfeld, and Merkovich-Vilonin tells us that this tensor category, this symmetric monoidal category, is the category of representations of the dual group. So this is where the dual group is born from the point of view of geometric Langlands. It's Tanakianly reconstructed from this tensor category. So that's the abelian story. This commutative tensor category is identified with representations of the dual group. So these are these kind of 't Hooft lines, and these I'll call Wilson. I'll write more about them in a second. But again, I'm mostly focusing on the automorphic side. Okay, now it's very important for our story to see this non-commutativity. In Akshay and Yannis's talks, there was Poisson structures around. And you can ask, where did these Poisson structures come from? And you don't see them in usual geometric Satake. But you do see them if you replace this geometric Satake by its derived version. So here, by the spherical Hecke category, we really mean the whole derived category, the equivariant derived category of the correspondent. So the derived category of sheets on this double coset space. And the derived version of geometric Satake, which is the theorem of Bezrukavnikov and Finkelberg, tells us that this category is identified with coherent sheaves on the coadjoint representation for the dual group. So I look at this vector space, the coadjoint vector space for the dual group, and I'm looking at equivariant coherent sheaves on there. Okay. So for example, inside of there are sheaves coming from representations of the dual group. If you like, pulled back from point mod the dual group, this space maps to, so equivariant sheaves always have, you can always tensor by representations of the group. So that's where the classical Satake lives. You see representations of the dual groups appear here, but you have this extra direction, this coadjoint representation. Secretly, it's in cohomological degree 2. There's a cohomological shift that I'm going to suppress. Okay. But there's a grading shift. But so the derived geometric Satake tells us that the spherical Hecke category actually sees the coadjoint quotient of the dual group, not just the dual group. So now you can really feel the non-commutativity of the factorization. Well, G-check dual is a Poisson variety. And there's a Poisson bracket on function there. And that Poisson bracket, you have to translate it, but it gives you a structure on this category of coherent sheaves, which is a kind of a non-trivial Poisson's structure. So I haven't defined what I mean by Poisson category. If you like, there's a technical definition of what I mean is an E3 category. This was observed by Lurie and Gatesbury, this structure in derived Satake. But the structure really boils down to knowing the Poisson bracket on functions on the quadrant representation. So this line operators in geometric Langlands are really not commutative. They're kind of Poisson. There's some shadow of non-commutativity. And if you want to define it rigorously, you can do it again in the two ways. You can either define a secondary kind of operation by moving one point around the other, kind of a monodromy or grading operation, or you can just do everything equivariantly for GM. If you study GM rotating the disk, if you study that GM equivariant deformation, you see the non-commutativity appearing. Okay, so what's important for me is that there's a Poisson structure in geometric Satake. And that's, again, fundamentally where the Poisson structures in our work will come from. Okay, great. So that's now I've done Langlands and geometric Langlands in nutshells. So now what I'd like to talk about is periods. So how do periods fit in this formula? Okay. All right. So once you put in a language like this field theory, there's natural questions you start asking yourself. For example, do field theories form a category? So what is the notion of a morphism between two field theories? In physics, these things are called domain walls. They're the kinds of defects that physicists like to study. But there's a notion of morphisms between field theories, these domain walls. And by here, I'm going to just take kind of maybe the most obvious idea of what you might think about a morphism of two field theories. You have these field theories where some kind of functors, and you can just think of natural transformations between two of these functors. In other words, a field theory is a bunch of assignments of different structures to different, you have curves with points and various things, a whole bunch of structures. A morphism of field theories is going to be a map between what one theory assigns to any of these things and what the other theory attaches to any of these things. Okay. So you can think of that as a setting for Langlands functoriality. This is naturally a place where you can talk about the functoriality of automorphic forms between one group and the other. So think of it as morphisms of field theories. But as it appeared in Akshay's talk, when we talk about like the theta correspondence, you can think of turning a morphism, the functoriality between G and H, you kind of rotate it. So a physicist would draw it this way. You have G and H. You can think of some wall separating G and H, or you can kind of turn it around. And I can't really draw three-dimensionally very well, but you can think of G times H, and you can think of a boundary for G times H. So this is the mechanism that Akshay said, how to relate periods with functoriality, like the theta correspondence. So basically, to say that the most essential case, you can boil down a lot of things to studying what we'll call boundary conditions. And a boundary condition here just means a morphism from the trivial field theory. That's all a boundary condition is. It's a morphism from the trivial field theory. What is trivial field theory? Everything in sight was symmetric monoidal, so that means you have a lot of units around. So it's just the thing that assigns the unit everywhere. That's what the trivial field theory is. Okay, so a boundary condition is going to be a morphism from the trivial field theory. Now, what does that mean in practice? And what I'm going to try to convince you is that it's exactly, you see all the structure of the kind of relative Langlands program appearing naturally just by asking this question, all the key features. So what does a boundary condition give you? Well, okay, to a closed surface, so now I'm again thinking in the topology setting rather than the curve setting. To a closed surface, we had an invariant Z of sigma. Now, a boundary condition will give you a map from the unit to that. That just means an element. So if you have a vector space attached to a closed surface, now we'll have an element in that vector space, a vector in that vector space. You had a category or some other kind of object attached to a circle, you'll now get an element of that. Okay, so you're attaching elements of everything in sight. That's what it means, a map from the trivial theory. So for example, then you can ask what happens to correlation function. So you look again on a surface minus some points. What does this give you? It gives you a map. In what you translate this definition, it gives you some map. It's a map inside of this category, the object attached to, you have a bunch of circles. To them, you attach some object. That's this tensor product of Z of these circles. But in this, you have two different things. You have the invariant attached by the full theory to the punctured surface, and you have the tensor product of the local invariants attached by the boundary condition, and you need to give a map between them. So again, I'm not telling you something, this is just follows immediately just from thinking what a natural transformation of these things is. Okay. So hopefully that'll look a little familiar to theta series. And finally, you could do something a little more rich, is for any open subset or for any input of your theory, you can try to pair. You can try to go from the unit to Z and back. If you like, make a kind of a sandwich, and you get a new field theory. This is for every U, you get a new object, but kind of one dimension down. Before now, it's valued in the C bar instead of in C. So these pairings form a field theory of one dimension lower. Okay, so again, I'm not going to focus too much on this. There's a lot of structure here, and I don't expect it all to kind of make sense. I just want to throw at you that there are a lot of natural things that you get just by asking for this field theory. Now I want to match it with the things that appeared in Yannis's talk. Okay, so now, how does this match with what appeared in Yannis's talk? Periods are going to give boundary theories for the automorphic TFT. So there's going to be analytic issues at the level where we're going to try to actually get numbers. These analytic issues will go away in the geometric Langlands setting. So I'm going to kind of ignore them up to now. So the arithmetic part is a little formal, the same issues of analytic integration and so on. So what's the idea? So given a spherical variety, or the kind of hyperspherical, the kind of Hamiltonian space version, let me just focus on the X, then we're going to get a boundary condition for our automorphic theory. That's our proposal, is that you should think of the data of periods, the data that defines period, these X's or these M's, as defining a boundary theory. So how does that work in classical Langlands? Well, on a curve, we had a vector space, the space of automorphic functions. We're going to get an element of this, which is the theta series associated to the unramified theta series, or ramified X period. So again, I'm using duality. I can think of it as a functional on automorphic forms, which is applying the period, or dually think of it as an element. In the local setting, we attached the category of smooth representations, and I'm going to give you an object of that category. Look at, say, smooth functions on X of F. So the same data of F defines a period globally. It defines a representation locally. These are part of the data of this boundary theory. I'm giving you assignments inside of the A theory on every input. So all this other structures in main players in Yannis's talk can also be said this way. Again, this is a lot of structure, so let me not dwell on all of it. But for example, the basic vector in Yannis's talk, we had the constant function 1 on the arcs into the spherical variety. That's what we attach to the disk. The element, so we have the element attached to this local field inside of there. This is functions on X of K. Inside of there, you have a distinguished function, which is what attached to the disk with boundary of the punctured disk. Okay, so that's the picture of the basic function. You can also see the theta series, or the adelic version of the theta series appearing this way. you can also see these pairings give the relative trace formula globally and the Plancherel formula locally. So all of these kind of players appear naturally just by asking this question for boundary theory. But I'm gonna kind of ignore, mostly suppress this stuff for now. I just want to get to my punchline. I promised you to construct the dual period, the spectral period, out of this data. Okay, that's my goal. So there's a lot of things you can do. You can formulate all the structures in the relative Langlands program this way. But my goal is to extract the dual. So first, let me say everything geometric, where the kind of analytic issues that I was suppressing go away. So in the geometric Langlands version, I have, instead of the period vector, I have a period sheaf. This is the period sheaf on Bun-G, the unramified Bun-G, X, this is what appeared in Akshay's talk by looking at maps into X, twisted maps into X, mapping down to G bundles. So there's a distinguished sheaf, the X period sheaf. That's an object in this geometric Langlands category. In the local Langlands, you get the local category, sheaves on X of K. That appears as that's the object attached to the puncture disk. That's an element of the geometric Langlands 2 category. So again, that's part of the field theory. That's what the boundary condition gives you. You also get the basic sheaf from Yannis's talk. There's a categorical version of the basic object, the constant sheaf on arcs into X. And if you like, there's also versions of all the other stuff in the geometric Langlands, but let me suppress it. So what I want to focus is on these guys. We have the period, and we have theta series, and we have this basic objects. Okay. Maybe I should stop for a second because I feel like I'm talking very fast. Were there questions, or maybe I talked too fast? Were there any questions?
I don't see any questions on YouTube.
Okay, I guess I talked too fast.
Sorry, I think one thing maybe. I got a little bit behind here. So here, what is X now?
Oh yeah, so X, the idea is X is a spherical variety. X, X is a spherical G variety, or maybe we should think of M, a Hamiltonian G space, plus this data of automorphic quantization that appeared in Yannis's talk. It's easier to just think about the X. So X is a G space, and it's going to have to be a spherical G variety for a lot of these things to be well-defined. Mm-hmm. So I start with a spherical G variety, and the claim is that the way I want to think about what this gives me is it's a boundary condition. It's this collection. So this theta X, this is what I'm thinking is a boundary condition for the automorphic topological field theory. It's a data, it gives you in particular for every input of the output of the field theory, I get a particular vector, a particular object in it. So the claim is that this perspective unifies the theta series operators, the RTF, all these objects. They're all aspects of they fit into just this notion of a morphism of field theories.
I see, and this is a theorem somehow, that this is really a morphism of field theories.
Yeah, I mean, the way I've formulated a morphism of field theories is extremely weak. I mean, so I'm asking for something compatible with factorization. So, I mean, I haven't formulated, for example, the data of bluing at the boundary. Right. And so that would have to be a theorem. That's a conjecture you can make. That's something that doesn't appear much in geometric Langlands, is really the study of nodal degenerations. And that's really where the cobordism composition part comes in. So that's a deep thing, and that hasn't been proved in essentially any context in geometric Langlands. So you can say this is a conjecture. Okay. But what I'm telling you is how to fit all of the different aspects fit naturally into this structure. And the basic compatibilities that I formulated, compatibilities with factorization structure and things like that, are kind of evident.
Okay, thanks.
Yeah. So that's how I want to think. So that's our proposal here, is to think about these varieties as defining boundary theories. And so first of all, that's already nice because it's organizing a lot of structure in a simple way, formally simple way. But the main interesting thing for us is that what I want to use is to construct the dual. This is how to see duality from this. And this is somehow the main punchline. The whole of my talk was just really building. I just wanted to get to this thing. So what I want to do, I want to look at these bubble operators, these line operators. I have these H's. So I attach these algebras. Remember, any field theory, we have this algebra of line operators that correspond to thinking about these kind of Hecke modifications. That's something abstractly to the field theory, and you can think of it as some endomorphisms of an object on the disk. Now, I said a boundary condition gives you an element of everything inside. Everything that any structure you have in a field theory, you get a part of it coming from the boundary theory. So in particular, if you have a boundary condition, you evaluate it on the ravioli, it'll give you an element of this HZ, which carries all the same structure. So it's compatible with all the maps. So what does that mean? HZ, this Hecke algebra, had an associative multiplication, had a factorization. So together you can think of it as some big Poisson algebra beast. And we get an object in here that has the same structure. So you could, technically, it's what you'd say an associative factorization algebra object or the E3 algebra object. But it's easier to just say it's a Poisson algebra living in this Poisson category. So this category HZ has exactly the structure that makes sense to talk about Poisson algebra in it. And it just follows from the formalism that if I have a boundary condition, I'll get such a Poisson algebra out of it, just by looking what it does on these bubbles. Okay, that's completely formal. What does that give us in our case? Let's apply it in the setting of periods. So again, remember, in the setting of periods, these bubbles, these line operators, is a spherical Hecke category. Okay, it's this sheaves on double cosets. So that I said is some kind of Poisson category. So this guy is going to be a Poisson algebra in this category. That's just, again, formally what we're supposed to get. Okay, what is it? So we have to think through the definitions. The definition tell you that this object is given by some endomorphisms of a unit. So when you think through what that means, so here's a formal kind of thing you could say, it's given by some endomorphisms of the object attached to a disk in some TF. So this is telling you some TFT picture for it. What does it mean in our case? It's exactly the object that appeared at the end of Yannis's talk. It's telling you that this algebra is endomorphisms of the basic sheaf. So Yannis said on the affine Grassmannian, on this space, the arcs into X, there's an equivariant sheaf called the basic sheaf, the constant sheaf on arcs into X, that appeared as a kind of categorified or geometric form of the Plancherel measure. Under the function sheaf correspondence, this gave us the Plancherel measure for X of F. Now we're saying that this categorified Plancherel measure, this geometric version of measure, is exactly this endomorphisms of this basic object. That's exactly our Poisson algebra. So in particular, what you notice out of this is, first of all, it's Poisson algebra. This is something that's not clear somehow from just thinking of pure thought. Where is this Poisson structure? But there's a Poisson structure on endomorphisms of this basic object. But it's actually more. It's a Poisson object in this category. So again, what does that mean in practice? Well, we know what these objects are classically. So now we use geometric Satake. Geometric Satake tells us the spherical Hecke category are just equivariant sheaves on the coadjoint representation for the dual. And I'm translating to the dual side. So this tells me that my algebra, my bubble algebra, is a Poisson algebra living over the coadjoint representation. So now take spec of it. If you take spec of this, you get a Poisson variety with a moment map. So really, I'm doing relative spectrum. I'm getting M check mod G check. So if you'd like, I'm thinking of, I have a Poisson variety M check with a moment map, which is equivariant. And what I'm really getting directly out of this construction is the equivariant version. I'm looking at the quotient M check mod G check with its equivariant moment map. So you just extract that directly as the spectrum of this local algebra. It's just this relative spectrum. So this is somehow the key point, is that starting from this automorphic field theory, you can construct, by looking at this Hecke operators on the boundary condition, you can construct a Hamiltonian G-dual space. Now, notice I'm not saying, when I say Hamiltonian, I'm not showing here that M check is symplectic, but it comes naturally with the Poisson structure. So it's a natural Poisson variety with a moment map, which we expect to be symplectic. So this is some kind of translation of the kind of thing. This is closely related to structures that you may have seen in the works of Braverman, Finkelberg, and Nakajima, theory of Coulomb branches. And this is inspired also by, again, I should mention the work of Gallardo and Witten on duality for boundary conditions in Yang-Mills theory. So let's try to put it all together. So what we're saying is that from a period, you get the structure of a boundary theory. From a boundary theory, among other things, you get a Hamiltonian G-dual space. So what we're conjecturing is that this Hamiltonian dual space is exactly the one that Yannis and Akshay told us how to build explicitly. There's a kind of an algorithm. This is the formula that appeared in Yannis's talk. You construct a subgroup of the dual group and a symplectic vector space, and there's some unipotent data that has to do with orthoparameters. So they give us an algorithm to construct a space. In their talks, it wasn't immediately clear why this should be a Hamiltonian G-dual space. Well, I guess in this picture it is. I've given it a picture as a Hamiltonian space. So I guess the point is that this agrees with the object that appeared as G check cross GX check, this W. Anyway, so the first conjecture you could say there's kind of a matching, that the thing that we get this way matches what you can build explicitly out of the theory of periods. And kind of maybe a stronger way to formulate that, the kind of local conjecture. So I have a few more minutes, is that right? Or?
Yeah. I have a question, so I don't know if it's a good time to ask.
Yeah, sure.
Yeah. It's from Jace. Can you say what the Poisson algebra structure is explicitly?
Well, there's explicitly the easiest way to get at it. Well, I don't know what I don't know what explicitly means. I think if you ask Akshay and Yannis, you get a very different answer. But let me say explicitly, formally, is that this construction. So Yannis gave us a construction which is some derived endomorphisms. I don't know what it was. We look at some derived endomorphisms of this basic object. Where does the Poisson structure come from? The easiest way to see it, well, it has an associative multiplication. That's clear. It's endomorphisms. You can check its commutative. That follows from factorization, but it's a commutative algebra structure. But where you see the Poisson is this carries a deformation. I can deform this. I get a one parameter deformation of this by repeating all the same formulas GM equivariantly. So everything here is equivariant for GM acting by rotations of the coordinate of the puncture disk. So there's a GM action. That means there's a deformation. There's a one parameter deformation. If you have a commutative algebra with a one parameter deformation, that defines the first order data defines a Poisson bracket. That's not my preferred answer. My preferred answer is to say that this data, you could get this notion of associative factorization algebra. This endomorphism has both an associative product, which is evident, and it has a factorization structure. You can do it factorizably as points move along the curve. And an associative factorization algebra, the cohomology of an associative factorization algebra is a graded Poisson algebra. That's that's what these E3 algebra things are. So that's somehow a more formal, for that's harder in that you need to talk about factorization, but it's somehow the right structural thing to say. But the easiest thing to say is just you have this deformation given by the GM equivariance.
David, in this slide, when you say
which one?
Plancherel measure, you really mean just the inner product, right? So the Plancherel measure will be seen on the dual side.
Well, I mean, this encodes, right? I mean, this is the codes, the traces of. Sorry, I'm just copying from your talk. So, I mean, this is the dual side. I mean, this is the dual side, right? I mean, I'm just saying that you're seeing this gives you kind of the endomorphisms between the unit object and the unit object tensored with any representation of the dual group.
Yeah.
That's because I'm thinking about not just an abstract Poisson algebra, but as a Poisson object in the spherical category.
I see.
So it's really encoding the full
structure of the action of the spherical category. Thanks.
That's right. Yeah. So maybe to emphasize here, the point is that this space is not appearing on its own. It's appearing with the moment map. And geometrically, that means the action of representation. So that's really giving the Plancherel measure. So this is the geometric version, what I learned from you guys of the Plancherel measure. Okay. So let me now state Akshay made me promise to state the local conjecture. So here's a conjecture you can make. You can forget about everything I've said. What I've said was try to give a way of how to get this dual space. But once you've gotten it, you can make this is the unramified local conjecture. I should emphasize this is kind of the unramified version. And what it says is that you look at sheaves on your spherical variety, G of O equivariant sheaves on the spherical variety, and that should be identified with coherent sheaves on this dual Hamiltonian space. That's what our duality is telling us. this is kind of a fancier version of what I was saying before about the algebra of functions, saying that sheaves, if this is indeed affine, category of sheaves just means modules of the ring of functions. So this guy is supposed to be affine over the coadjoint representation. So sheaves just means I just need to give you the ring of functions. But in any case, the local conjecture tells me that so this is one of our main conjectures, is that the category of sheaves on the X of F is identified with sheaves on, so these are G-check equivariant sheaves on the spectral period. And this is compatible with a whole lot of structure. So for example, there's a Frobenius action on the automorphic side. This should match with the natural grading that appeared in, I think in both talks. There's a natural GM action, which is giving kind of grading. Both sides carry actions of the spherical Hecke category. Thanks to geometric Satake, you can identify actions on both sides. This should be compatible with them. And the feature I've been using is it should match Poisson structures. The Poisson structure on the right-hand side comes from this factorization structure, the kind of non-commutativity of Hecke multiplication on the automorphic side. So this is somehow the strong version of this is our strong local conjecture that ties together the geometry of the spectral period with the geometry of the harmonic analysis, if you like, on the spherical variety. And let me just conclude with the last slide is that really what we're saying here is there's a package. I didn't spend a lot of time on the spectral side. But really what we're saying is that under the Langlands correspondence, we should think of as an equivalence of field theories. I didn't tell you much about the B theory. We can say more if there's questions. But the Langlands correspondence is equivalence of these big packages on both sides as field theory. So it matches all the structures. And what we're saying is that the period associated to a spherical variety is going to be identified with a boundary condition on the B side, which I would call kind of an L function, or this is the spectral period. It's something that will spit out L values, but it has a lot more structure. This is the data attached to this Hamiltonian G dual space. This is the data attached to Hamiltonian G space. And what we're saying is that all of the structures on the two sides, so there's local, global, geometric, arithmetic, ramified, so on. There are many conjectures that this is encoding and many compatibilities. We're saying that this kind of theory of L functions and the theory of periods in this strong sense are identified under this equivalence of field theories. And that's kind of the meta picture of how we want to think about periods. Okay, thank you very much.
Thank you so much for your fantastic talk. So it's time for questions.
David?
Yes.
Yeah. So I may have asked you this question in the past already, and I think you did give a good answer, but I probably forgot. So this business of this Hamiltonian G space giving you a boundary field theory, this doesn't seem to be something from I can read anywhere in Kapustin-Witten or Gayotto-Witten. Is that right?
Oh, you can read it in Gayotto-Witten.
Oh, is that right? So it's in Gayotto-Witten.
Yeah, no, this is So Kapustin-Witten set up the basic paradigm. Well, Gayotto-Witten actually were not really studying necessarily the topological field theory. They were studying the full physical field theory. So it's kind of a richer setting. So there's not just like Hamiltonian spaces, they're actually hyperkähler manifolds with hyper-Hamiltonian action. So I mean, they have more structure around because they're trying to get something kind of stronger. But Gayotto and Witten studied boundary conditions. One of the awesome things they did, for example, it's really interesting I think for number theorists to look at Gayotto-Witten because you see things appearing through a kind of a funny mirror. So for example, they introduced these things called non-pole boundary conditions. This is one of the main objects. They introduced these funny, weird boundary conditions that appear that hadn't really been studied before. It's called non-pole. And they have to do with an SL2 triple and some kind of singularity of the fields. And the beautiful thing is these are exactly Whittaker conditions and their generalizations, the kind of Arthur SL2 data. So somehow they discovered Arthur SL2 for purely physical reasons. But they studied supersymmetric boundary conditions in n equals 4 super Young Mills. An example of this. So for them, Hamiltonian spaces are an example. Given a Hamiltonian G space, you can couple the sigma model of that into Hamiltonian G space with the gauge theory. It defines a class of boundary conditions. For them, there's all kinds of other ones. For example, non-pole doesn't immediately fit for them. They didn't think of it that way. But they think of Hamiltonian spaces as part of a bigger class of boundary conditions. So really, you might think that, I like to say that, you started with this, you had this period, which you had a subgroup H of G, and then you expanded it to X equals G mod H, and then you expanded to M, which is T star X, and then you might expand to some boundary condition, and maybe there are more of these. So that there might be interesting exotic boundary conditions. But one of the things, this process I explained to you, the spectrum of this bubble operators, whatever, there's a map. You can construct a Hamiltonian space out of one of their boundary conditions. It's called this Coulomb branch construction. So there's at least a shadow. There is a Hamiltonian space around for any of these boundary conditions. It might not capture everything in the physics, but at least they're, so on some course level, they're saying Hamiltonian actions of G and G dual define boundary conditions on two sides. Maybe they're not all of them. So you might ask, does the duality really take these to these? But you can make kind of stronger statements that any boundary condition defines a Hamiltonian space for the dual, and there's some close relation. So it's, sorry?
Yeah, I think I kind of understand, but I guess I didn't even know that the Coulomb branch defined a boundary condition. Is this something very standard somehow?
No, so the Coulomb branch is kind of a shadow. So this Braverman-Finkelberg-Nakajima story is something about three-dimensional field theory. They attach something to the Coulomb branch, which is Hamiltonian, it's just a symplectic space. There's no group around. Though they do more refined versions in their later papers. So that's a story about three-dimensional field theory. But now we're thinking not about a pure Hamiltonian space, not a pure symplectic space, but a Hamiltonian G space. So this extra structure. So that's not appearing. This theory of Coulomb branches, people are usually talking about 3D gauge theory. In 4D gauge theory, you're interested in the boundary conditions. It's not just a symplectic variety with a G action. That's how it couples to the gauge theory.
I see. Okay, I see.
And there's a relation between the two. It's not, so to speak, the same duality. It's a refinement. The 4D version is a refinement of the duality where you throw out the group.
I see. Okay. Yeah. Thank you. Yeah, that makes sense.
Oh, sorry. I was muted, so I apologize. Yeah, here's a rather long question from Tony Feng. The local conjecture implies that there is a distinguished way to promote the E2 structure to an E infinity structure. Is there a conceptual explanation of why this exists? For instance, is there a way to describe it internally on the geometric side without invoking Langlands duality?
Right. Yeah. Okay. So you Tony, of course, caught me at one of the places where it doesn't because I mean, what to say? If I stated the factorization compatibility carefully, so let me say it a little more carefully. This equivalence. So you can ask the same question in geometric Satake. Geometric Satake tells us that the spherical Hecke category is identified with sheaves on the coadjoint quotient, maybe with some shift up. Now, this category is sheaves on a space, so it has a symmetric monoidal structure. So you could say, by this equivalence, this category gets a symmetric monoidal structure, but that's the wrong one. The natural Hecke structure here, the factorization structure, is not commutative. It's kind of symplectically E3. It's non-degenerately, the Poisson structure is non-degenerate, it's symplectic. In some sense, so really, the way to think about it is that you should think about this as the cotangent bundle shifted by 3 of point mod G check. So it's really symplectic. It's non-degenerately Poisson. So saying that the symmetric monoidal structure on the right-hand side is not the right one. It doesn't match. So the left-hand side is only E3. And the same thing is going to be true in our conjecture. The left-hand side is only E2. This guy is, as you say, symmetric monoidal. So what's secretly involved here, and this is something that suppressing, there's something called, so to make the factorizable version of the conjecture, I need to polarize M check. If M check is a cotangent bundle, so that's kind of the simpler setting. If M check is polarized, then I could do what we call a spectral quantization. So you need to do a quantization on the spectral side, just like on the automorphic side. On the automorphic side, it's more familiar. It's had to do with wave representation and so on. On the spectral side, and this had to do with this issue of square roots that appeared in Akshay's talk. On the spectral side, you really need to, if it's polarized, I can give this category a canonical, I could give an E2 structure that matches the left-hand side. That's a correct conjecture to say. Without polarization, you somehow need to quantize the right-hand side. So yeah, so that's, and so that's one of the things that I think is very interesting, but we don't have a clear answer for. In the non-polarized case, how do you construct a spectral quantization? That's this kind of deformation quantization to this to just an E2 category. You can see that there is one if you believe the local conjecture. It's not clear how to see it intrinsically, how to construct such intrinsically on the spectral side, unless you're polarized. So the same kind of quantization, and in fact, there's analogs of, we think of the metaplectic representation, there are a lot of the same kind of anomaly issues that you see in trying to quantize on the automorphic side appear in their kind of funhouse mirror version on the spectral side as well. Hopefully that answered the question. So it's not there. There isn't a symmetric monoidal structure really naturally on the left-hand side.
Thank you. Well, here's another question from James Hathada. Is there generalization to affine or loop groups related to 60 2,0 theories, or further generalization in the setting of 60 little string theories?
Yeah, that's a great question. So I should say I understand very little about little string theories because they're not field theories. So that's sort of harder to see. A lot of the kind of structure that we're using is extended field theory structure, and little string theories are not little. So there's a lot of there's exciting math going on with them, but that doesn't have all of this structure. For the 60 story, you can see versions of these. For example, these Gayota-Witten boundary conditions that I was mentioning in Young, like these down-pole conditions and so on, they come from defects in 6 dimensions. So there are all kinds of beautiful structures you can see in 60, but 2 things to say. First of all, I don't see any relation to number theory at this point. There's beautiful relations in geometric Langlands, but I don't know in number theory where these extra dimensions might come up. The other thing to say is in the 60 version, there's no duality. I mean, the duality comes from compactifying this 60 theory on a torus. So it's not, you don't have 2 sides that you're saying are the same. You just have one 60 theory, and you can study lots of interesting things in there. So there should be interesting question about studying these, codimension 2 defects in the 60 theory. But this kind of duality story that I'm telling is really about 4D. I need to have duality to ask the kind of questions we're asking.
Okay, thank you. Also have a question. So I guess your local conjecture is at unreified places, perhaps. But yeah. I'm wondering whether there's a kind of precise conjecture at reified places.
You can try to make conjectures. So you can make conjectures sort of, what to say, it's hard to make conjectures that are not conditional on the local geometric Langlands correspondence. If you give yourself a local geometric Langlands correspondence, which is again a kind of a wide open conjecture, even its precise formulation is kind of very subtle. If you give yourself the local geometric Langlands correspondence, so that's something that relates, I don't have blank pages here. So so somehow you have loop group actions on categories, and then you have some roughly sheaves of categories over the stack of G-check local systems on the punctured disk. That's roughly the nature of local geometric Langlands. If you give yourself that, then you can try to match. So given a space X, again, let me be polarized. So not try to use M's, but use X's. Given a space X and a space X check, you can construct objects here. So, you could just look at sheaves on X of K, and you could look at something similar to this kind of fixed point kind of object, sheaves on this kind of fixed point stack, local fixed point space. So you can make conjectures like that. At least in our current version, I don't think we're planning to say anything like that in the paper because it's fanciful enough that it's hard to falsify because it depends on local geometric Langlands, and you don't really have a functor. You don't really understand how these two sides relate. So it's hard to test. In the Iwahori case, in the tamely ramified case, I think I don't think it's also not in the first paper, but I think we can probably make a precise tamely ramified extension of this local conjecture. The data is the same. So the nice thing about the unramified conjecture is it lets us extract the spectral period. Once you have this spectral period, you can then say, at least if it's polarized, you can then construct objects that make sense in the ramified setting as well, and you can make lots of conjectures. So I think the belief is certainly that the kind of meta conjecture I wrote here, this includes in it a ramified conjecture and a global conjecture with ramification. The data that needed on both sides is both given by this X and the M check. You can define objects, you don't have a lot of confidence in, other than just believing it's in beauty of method, that these things will match.
Yeah, if I can just add a comment. I think that's, as David said, there are many, we have some understanding of ramified periods, and I think our understanding of this story is not yet, it should be reproducing that, and we haven't. If you go past the Iwahori case, as David said, we don't understand it at the level we would like.
And meanwhile, I got a further comment from James, the previous questioner. Yes, I mean 6D theory on torus.
Right. So I guess depends what you mean by 6D theory on the torus. I mean, if you're doing, so you're asking, you're asking a question not in the Kapustin-Witten twist. So we're saying everything in the topological field theory setting, which is a twisted version of the 6D theory on the torus. If you want to do the untwisted setting, that's a fascinating question of what to do with the kind of the full physical theory. And I don't think that's really been explored anywhere in the math literature. It's somehow going beyond the topological field theory or beyond kind of maybe this partial holomorphic, partial topological twist. So there's, I guess in that setting, you could do something, the 2 dimensions holomorphic, 2 dimensions topological. But I think that's, and that's a version with like what's called Dolbeau geometric Langlands or semi-classical Langlands. And that fits in our story, by the way. You can do a semi-classical or Dolbeau version of our conjecture for periods and L functions. And that's something that seems to work very nicely. But beyond that, in the full physical theory, I have no idea what that even means mathematically.
Okay, thank you. So we are only 2 minutes away from the next talk. So I'd like to wrap up the Q&A session, and let's thank David again.
Welcome back, everyone. So this is the last talk of today, also last talk of this 2-day symposium. I'm very happy to introduce Dr. Jaeho Haan from KIAS, Korea Institute for Advanced Study. He's a postdoc research fellow there. He got his degree, PhD degree from Seoul National University and was a postdoc at KAIST. Then currently he is in KIAS. So he will start his talk. Let us welcome him.
Oh, thank you very much. This is a great pleasure and an honor to be speaker here. I thank Professor Choi and Professor Shin for the invitation, and thanks to any invisible audience for watching through YouTube. Today, I mainly talk about the application of the so-called regularized period toward the gangrenous process conjecture. My goal today is not to communicate the technical detail of some specific argument, but rather my goal is to give you some sense how things is going on, and with the regularized period, and I hope this general overview will be stored in your mind and come up with someday when this idea will be helpful. To keep you from paying much attention to the technical terminology, I postponed many exact definition of some terminology far behind on the slide I'm going to show you. For even though some unfamiliar terminology like residual representation, mixed truncation, and regularized period appeared, please don't scared. When some important terminology is needed to introduce, I will explain it later. So at first glance, please take it without no much stress. So I will begin my talk. I will first introduce some motivation of the regularized period. The managing of A values encodes deep arithmetic informations. For example, the managing of Dirichlet L function at 1 implies the Dirichlet prime number theorem, and the managing of the central A value of elliptic curve implies the finiteness of rational points of elliptic curve. It is implied by the famous BSD conjecture. So, many number theorists believe that every L functions arising number theorists essentially come from automorphic L functions. So, if we take this philosophy granted, then it is enough to consider only the L values of automorphic L functions. So often the non-vanishing of certain L values of automorphic representation is equivalent to the existence of some residual Eisenstein series representations. So, to show the existence of residual Eisenstein series residual representation, we want to consider each period of residues. When, for example, when EG is the residue of an Eisenstein series of ESG at S0, then to compute each period. One is attempting to compute the original, the period of original Eisenstein series and take its residue at S0. But unfortunately, the period of Eisenstein series does not converge in general. So to make sense of this integral, we need to regularize period integral in general. That is one motivation I'm considering the regularized period integral. And the global Gang-Gross process conjecture predicted the relationship between the non-vanishing of the central values of a certain automorphic L function and that of a certain automorphic period. And since my main interest, since the most my most interested values are the ones appearing in the Gang-Gross process conjecture. I will call it the Gang-Gross process conjecture as GGP conjecture for abbreviation. So since my most interested value is the one appearing in GGP conjecture, so I will express what does the GGP conjecture is. So to explain the GGP conjecture, let me first introduce the period for GGP pair. Let Gn a pair of classical or metapredicative group of rank m and n. Here m is less than n. And sorry. Here Gn can be the orthogonal group and Hermitian unitary group or skew Hermitian unitary group or symplectic group or metapredicative group. When n is some unipotent subgroup of Gn stabilized by Gm, and when n minus m equals to 1 or 0, then we assume we say n is the trivial group. I will not explain the exact definition of this unipotent group, but just take this group just as I just said, and write G, Gn cross Gm, and H is the semi-direct product of n and Gm. We call such pair G, H a GGP pair. And when m minus m equals to 0 or 1, and then note that H is a reductive group. And we have a canonical embedding of H into G by diagonal embedding. And let chi be a generic character of the quotient group of H or of n or H. When we consider this character as of H, then we think the value of Gm is trivial. And theta omega is an automorphic value representation of H. And we do not know which depends on the character of chi and unexplained character mu. It is divided into two cases. When m minus m is odd number, it is the chi. And when m minus m is even number, it is the automorphic value representation of H. And pi is irreducible cuspidal tempered representation of G, and it is decomposed as pi 1 times pi 2. And the pH for the element of pi in pi and f in nu, I define pH pi f as the period integral of the 10th product of these two functions on H. And then it is easy to see that this linear function pH is in the home space. Then I say the definition, and I will explain the definition of Bessel and Fourier-Jacobi period. When n-m is odd, we write the period pH v, and we call it the Bessel period. When n-m is even, I write fj for pj and call it the Fourier-Jacobi period. Then the natural question for these two periods is when b and fj are non-zero. The answer is there is two conditions. One is a local condition and the other one is a global condition. That means we write pi as a resistance product of pi v, and we also decompose du as a resistance product of nu v. Then this global home space is decomposed into a resistance product of this local home spaces. We think that these two functional as an element of this local resistance product of these local home spaces. Then in order to have these two linear functional is non-zero, we need to enlist all these local home space is non-zero for all places V. This is the so-called local condition and the local GGP conjecture concerns about this problem. And the global Gangros-Prasad conjecture concerns the global condition for the numeration of this period. The global Gangros-Prasad conjecture says that let G, H is be a GGP pair and pi is an irreducible tempered cuspidal automorphic representation of G. Suppose for all places V, this local home space is non-zero, and we decompose we decompose pi as a 10th product of pi 1 and pi 2. And then the GGP conjecture says that the Bessel period is numeration is equivalent to the numeration of the central L value of this 10th product representation. And when n-m is even number, the Fourier-Jacobi period in the diminishing is equivalent to their associated central L value. Rankin-Selberg central L value of Rankin-Selberg function is non-zero. So these are the conjecture of Gangros-Prasad, and it is a period 2012. So do you have any questions so far?
Not.
Yeah. Okay. Let me proceed. As far as I know, there are two different approaches toward GGP conjecture. One is the use of residual representation, and the other one is use the relative choice formula. Let me first introduce the approach using the residual representation. This approach was pioneered by the Ginsburg, Jiang, and Redis in 2004. They proved the one direction of the Fourier-Jacobi case under some condition. For more precisely, let pi via irreducible tempered cuspidal automorphic representation of metaparetic group of rank 2n plus 2r times the symparetic group of rank 2n. And they assume the following: the base chain, the Langlands functorial transform of pi to general linear group is cuspidal. It is equivalent to saying that the A parameter of pi is simple. So the original GGB conjecture is formulated. Their associated A parameter is tempered, but simple parameter is weak, is a special tempered A parameter. Then they showed when the relevant when the Fourier-Coby period is non-vanishing, then the central value the central value of the Rankine function is non-zero. Here the L function is the definition of this L function is the Rankine L function of the functorial liberty of pi. They used the Arthur truncation of Eisenstein fields, and then using that, they directly computed the period of residual Eisenstein fields, and they showed that the period is non-zero. And as a corollary, they showed this central value is non-zero from some philosophy, as I earlier mentioned, because the central value of some central value is concerned the existence of residual Eisenstein fields. And using this similar idea, they also proved the direction of one toward two direction of the GGB conjecture for orthogonal group and Hermitian unitary groups with simple A parameters. And after that, in 2014, Ichino Yamana found that there is a critical error in their proof for when the crank is positive. But their proof still work for the basic case. I call the basic case when the R is 0. That is, in the basic case, the crank is 1, and the Fourier-Coby case, the crank is 0. I call it both cases the basic case of the GGB conjecture. But Ichino Yamana detected that their proof is wrong. Not wrong. Their proof has some gap when the R is greater than 0, but their proof still works when for the basic case, that is R is 0 case. After observing such a gap, they proved the one direction of the basic GGB conjecture in two papers for the basic case for unitary group and the basic Fourier-Coby case for metaparetic symparetic groups. They improved the result of Ginsburg-Reyes by improving the simple A parameter to replacing the simple A parameter with tempered A parameter. So let me convey the basic idea of their method. Their basic idea is inspired by the paper of Jacques Rapid-Reyes on the regularized period integral. in 1999 and 23, Jacques Rapide and Jacques Rapide developed the theory of mixed Author truncation and regularized period for special reductive pairs, such as Gn has some symmetry and H is the fixed subgroup of such symmetry. For example, G is when E over F is a quadratic extension of number field, say G is the extension of GLE and H is GLF. And inspired by the Jacques Rapide regularized period integral, Ichino Yamana invented the mixed Author truncation and regularized the period for the basic GGP pair for Gn plus 1 times Gln, Gln, and Un plus 1 times Un, Un. And subsequently, Yamana developed a similar machinery for the basic Fourier Covey GGP pair. That is MP2n times SP2n, SP2n. Using as an application of the regularized period, they proved the vanishing of the regularized period involving Eisenstein series in a conceptual way. The Jiang and Rallis study also computed the period of truncated Eisenstein series, but their computation is rather involved. But using with the help of this machinery of regularized period, they computed the residual Eisensteins in a very conceptual way, conceptual and in neat way. And I will also introduce another approach using the relative trace formula to a GGP conjecture. In 2040, Wei Zhang proved the basic best case for unitary group. Let me recall his result. Let pi be an irreversible tempered hospital automatic representation of Un plus 1 times Un. And we assume the two local assumptions. One is all Archimedean places of F split in E, and the second assumption is a base change of pi v is super hospital for some finite place V. Then the following are equivalent. When the generic character is trivial here, the best period is vanishing is equivalent to the central average non-zero. So they proved the GGP conjecture under these two assumptions, local assumptions. And after that, the Heng-Shu proved the basic Fourier group case for square Hermitian unitary group. But since his result is take the similar strategy of Wei Zhang, his result is also conditional. These two conditions. After the appearance of this result, Heng-Shu and Bujat Precious removed the first local assumptions independently, but it is believed that to remove the second assumption is very difficult. But in 2019, Bujat Precious, Wifeng Liu, Wei Zhang, and Xin Wenju has weakened the second local assumption to that base change is capital. So with this result, they proved the basic case of GGP conjecture is proved with simple A parameter. But very recently, the amazing result has appeared. That is, the Bujet-Precious and Shodard and Jaeho proved the endoscopy case of basic basic case completely, since the tempered case is contained in the endoscopy cases. They proved all tempered case of basic GGP conjecture and some non-tempered endoscopy case of GGP conjecture. So this result is very strong. So this so far I summarized some results on the basic case of the GGP conjecture, and let me turn into the non-basic case of GGP conjecture. On the basic case, there is some result of Furusawa and Morimoto that they proved 1 to 2 direction of the GGP conjecture for SO 10 plus 1 times SO2 for some special tempered representation, where pi2 is an automorphic character, one-dimensional representation of SO2. And very recently, there is a big progress of Jiang and Zhang in 2020. They proved the 1 to 2 direction of the GGP for both special orthogonal groups and unitary groups in full generality. They did this by computing the computation of the global zeta integral defined by the Bessel period involving Eisenstein series. But their result is still conditional because they presume the computation of the local zeta integral at unramified places. So, but in the paper they also proved the converse direction under certain circumstances. So, and I think their assumption of the computation of the local zeta integral is not so much hard. So I think they are writing some papers about this computation of local zeta integral. And for the Fourier-Jacobi case, Gilbert Rogoski studied the Fourier-Jacobi period for U3 times U2. That is the Corinth is 2. And Ginsburg, Jiang, Rellis, Liu uploaded the correction of the error in the 1 to 2 direction proof of the GGP for metaplatic and sympathetic group when R is greater than 0 case. Because some gap was detected by expert, and they corrected the error in 2019. So that is the progress for the non-basic case as far as I know. And so to attack the non-basic case of the GGP conjecture, my work is to attack the non-basic case of Fourier-Jacobi case for skew Hamiltonian unitary group, and there are 2 choices to use relative trace formula or residual, or use the residual representations. I used the residual representation approach, but I did not follow the Ginsburg, Jiang, Rellis approach, but rather Ichino, Yamana, or Yamana's approaches using the mixed truncation. So to attack the non-basic case of GGP conjecture, we first developed the theory of mixed truncation and regularized period for G, H when the H is non-reductive group, or when n minus m is 0 or 1, n it becomes trivial, and so the H is reductible. But to consider the non-magic case, we consider this non-reductive group. And it is worthwhile to mention that the Jaeho developed a mixed truncation and regularized the period for general reductive pair G, H, generalizing the theory of Jaeho rapid release. But his result works on when H is only reductive pair. We cannot use his mixed truncation and regular period. So I should develop some machinery for G, H when H is non-reductive, some special non-reductive group. So let me introduce my result, one of my results. When G, H is Gn and Gn, n times Gm. Here, Gn, Gm is classical or metaplate groups. And Agn, red Agn is the space of atom forms on Gn. And I defined the space of atom forms on n times Gn. When the n is Heisenberg group, there is a typical example of atom form of this space that is called the Jacobi form. So models based on the property of Jacobi form, I defined the space of atom forms on this reductive group, modeling the Jacobi form. And the original alpha truncation is defined on the space of a smooth function with very weak restriction, but I confined myself to the space of target space of mixed truncation on the atom forms on Gn times atom forms of n times Gm. So for these two, for the pair of these two, for the pair of functions in this space, I defined the mixed truncation which send this pair to a rapidly decreasing function on Gm.
Excuse me, n is an arbitrary unipotent group here?
Here, no. In this setting, n is, sorry. Yes, it is an arbitrary unipotent group which has a Gm action.
And does it have any data like a character or something like a Whittaker character or veil representation, or no data like that?
No, it is general definition.
Okay, thank you.
Yes, but it is modeled the veil representations and theta functions. And after defining the mixed truncation, I defined the regularized period using this mixed truncation. So I will omit the detailed definition of this stuff. Then the regularized period I defined has the following properties. When pi1, pi2, pi3 is integrable over this product space, this product group, then the regularized period of these functions is equal to the original period integral. That is why the regularized period I defined is a natural generation of original period integral. And in order for P regularized period deserves to the name of regularized period. regularized period, it has the property that it is right NA times Gn invariant because this period integral has this property, and since the main reason for develop this period integral is to define something like period integral for involving the Eisenstein field. So my definition of a regular period is well defined for when it involves some Eisenstein field, but except for the poles of Eisenstein field. But this function on C has some Belomorphic continuation to the whole complex plane. So this is third property is one of the new property which regular period has. And using these properties of regularized period, I show that the regularized period involving some residual Eisenstein field is non-zero since the existence. So from this we know that some residual Eisenstein field exists, and it leads to the nomination of central value. So as a result, we have when n minus m is to R, then the nomination of a Fourier period implies the nomination of the central value. That is my main result.
Does your regularization generalize the one of Zidore when n is trivial?
No. My regulation works for only classical groups, but Jaeho's regulation works for general reductive group G.
But does it have the same shape as his when the groups are classical and n is trivial?
Yes, I did not check. I did not read the definition of Jaeho's regular period, but I think
so your method is different. Your method of regularization.
Yes, different, but I think these two mixed expressions are same for the when the n is trivial and GM is a classical group. I think these two definitions are same.
Can you say something about the idea of the regularization? How do you regularize the integrals?
The definition of a mixed regularization?
Yes, maybe. I don't know. I don't want to derail you, but if it's easy to just give a sense of how you perform this regularization.
Yes, I postponed the exact definition of regulation far behind of my slide. So
okay. That's fine. That's fine.
Permit me, I will show the definition.
Okay. That's fine. Thank you.
So from now on, I sketch the idea of the proof of this my main result. To prove the main result, I use the following key properties of pi 1 and pi 2. The first one is the base change of pi 1 and pi 2 exists, and the base change of pi 2 is decomposed as an isobaric sum of sigma 1 and sigma t, where sigma i's are all distinct irreducible Cospedal automorphic representation of the general linear group, such that the associated outside L function associated to its outside L function has a pole. And the third property is the local normalized intertwine operator is a holomorphic for all G, where with the real part of G is equal or greater than 1/2. 1/2. These properties follow from the temporaleness of pi1 and pi2 because it ensures that the endoscopic classification of automorphic representation of unitary groups for quasi split done by Bob and non-quasi split Kalesa, Minguez, Shin, White guarantees that the temporal representation pi1 and pi2 have the above three properties, and I used these three properties crucially in the proof of one direction. Right. There are two choices of decompose pi1 or pi2, but I choose to use the isobaric sum of pi2. So we write the base change. We write the base change of pi2 as an isobaric sum of sigma i's. Then the central value of this Rankine self-L function is the product of this base change pi times u inverse sigma i's. Is the L value of this. The central values of this representation. So, and the one of the lemma of Ichino Yamada paper is that when sigma is cuspid automorphic representation of GLA, such that sigma, the associated L function of sigma has a pole at S1, then and pi is a irreducible temporal cuspid automorphic representation of UN, then its central value of the associated L function is non-zero if only if its relevant to Eisenstein series is non-zero. So this lemma, this type of lemma was first used by Ginsburg and Ginsburg-Reyes GM paper, but all of these kinds of lemma comes from the Langlands theory of Eisenstein series, because the analytic behavior of Eisenstein series is controlled by the constant term of Eisenstein series, and the constant term of Eisenstein series is pertains to the intertwining operator, and the computation of intertwining operator at unramified places is well known. So this lemma comes from the basically essentially Langlands theory of Eisenstein series. So to show this Fourier-Jacobi integral is non-zero, then we should prove all these central average is non-zero, and by this lemma, the nomination of this L value is equivalent to the existence of residual Eisenstein series. So we are enough to show that all these residual Eisenstein series exist for all i's. So but I did not explain what the definition of residual Eisenstein series, because it requires a bunch of some terminology and definition. So from now on, I will introduce some terminology for explain the residual Eisenstein series. So to speak of it, I introduced the Eisenstein series first, but to define the Eisenstein series for unitary group, it needs some bunch of notations. But since I'm running out of time, so I omitted the explanation of these notations. But I think many experts are familiar with these notations, and so once once we can Eisenstein series, then we have such a proportion. Red pi is pi via irreducible temporal hospital representation of UN, and sigma is irreducible hospital automorphic representation of GLA. And when the automorphic when pi is an automorphic form of U2A plus n, which comes from the hospital representation of sigma times pi, then the associated Eisenstein series of pi has a most simple pole at G is 1/2 or 1. So it's not so hard proportion. So since this Eisenstein series has a most simple pole at these two complex number, we can define their residues, and I will write the residue of this Eisenstein series at 1/2 as E0, and its residue at 1, right, E1, and the space of these two residues for each I call it. I will write. I will denote their space EI sigma comma pi, and I call it the residual representation of U2R plus A generated by these residues. That is the definition of residual representation. Then, since to prove our main result, to prove our main theorem, I already mentioned that it is enough to show the existence of these all residual representation vanishing. So how we can show the existence of residual representation? The one way is to compute their period and show that if we know that the period of residual Eisenstein series is non-zero, then it says that the residual Eisenstein series is non-zero. So to prove our main result, I proved this theorem. That is, red sigma is isomorphic to one of the isobaric summand of sigma I, or isobaric summand of base change of pi 2. Then when the Fourier-Jacobi period of pi 1 times pi 2 is non-zero, then the relevant regularized period involving this residual representation is non-zero. So by proving this theorem, we know that this residual representation is non-zero, and it proves the relevant central absolute is non-zero, and it proves the one direction of GGB conjecture. So let me let me how to prove this regularized period of residual Eisenstein series is non-zero. Let me explain. I already mentioned that the regularized period has the three properties. The first and second is natural for the naming of regularized period, but the third one is the new one for the regularized period. But there is one more hidden property of regularized period. That is the period of regular period of this function is related to the stuff of these two functions. Though even though I didn't explain the notation and the definition of these two stuff, but just take it for a while, and I want to mention that this fourth property is hidden from the original definition of a period integral. But if we define the regularized period, this hidden property appears when the regular period is adequately defined. So I used this hidden property of a regular period to connect to relate the period of residual Eisenstein series with the regularized period of Eisenstein series. So to compute the regularized period of residual Eisenstein series, we should connect it to that of original Eisenstein series. So, but to connect these two periods, to state the relation of these two periods, I need one more notation, and it needs I should introduce some notation. So the notation is temporal, so not so important, but to state it, it is necessary. We write PA for this parabolic group of rank n plus 2a. For abbreviation, I will write these groups as just PA, MA, and A, and let PAK with the Iwasa decomposition of U n plus 2A. Sorry. So the unipotent group N appeared in the original Fourier period is N, but the unipotent group appeared in this regular period is, I will denote it N prime. So you can see this period as some amplified version of this Fourier period, because in the left hand side, something like the representation of GLA is multiplied in the left hand side, so it can be regarded as an amplified version of this original Fourier period. So the relevant unipotent group in this period is denoted by N prime, while the unipotent group in the original Fourier period is denoted by N. There is some subgroup V in N prime such that the N prime is decomposed by N times V, and then for fixed element of V and K, like we write small V and K, and for the automorphic form of U n plus 2R and pi and psi for automorphic forms of U n plus 2R and U n plus 2R, and fix an element in the value representation F. We put PV, we temporarily define the period associated to the choice, the fixed choice of VK, PVK, as like this. PVK pi psi F is defined like this integral. So the one observation is that the diminishing of the original Fourier-Jacobi period integral, Fourier-Jacobi period for this representation is equivalent to the diminishing of the period integral of P11 of these representations. So here V and K is the identity element. So this is not so hard observation. So the dimension of these two periods is equivalent, and because yes, so using this notation, then I can rewrite the regularized period of residual Eisenstein series to that of Eisenstein's original Eisenstein series. So for pi and psi and theta f in the relevant automorphic space, then the regularized period of residue times residue of pi times psi, comma theta f is decomposed into some of two pieces. The one is the residue of this regularized period of Eisenstein series at 1/2, and plus the integration of my ad hoc period integral times some exponential function on v and k. So it is decomposed into two parts. So this lemma shows that the relation of the residual period and Eisenstein series period, but their difference is this one. And since I remarked that the dimension of Fourier period is equivalent to the dimension of this period when v and k is equal to 1, then so from this condition, we can find pi and psi and f such that the integration of this ad hoc period integral times some exponential function over v and k is non-zero. Since though I mentioned that the dimension of this period implies the dimension of this period when v and k equals 1, but if we take the support of pi and f sufficiently small near 1, then we can ensure this property from the dimension of the p1,1. So this is the second lemma. So we know that from our assumption, this second part is non-zero. So so our third lemma is the I call it the vanishing lemma, is that for the three function pi, psi, theta phi, the regularized period of Eisenstein series is always 0. This is the most hard part in the proof of my result, and I call it the vanishing lemma. The proof of this should be separated into two cases. When it is separated according to the m minus m is 1, m minus m is 0, or is positive. When the m minus m is 0 case is almost similar with Yamana, because Yamana proved this for metapolitic and symplectic group for the basic Fourier case. So we can follow his proof similarly in this basic case. But when m minus m is a positive case, we cannot follow his proof. So it requires a more involved computation and argument. One observation is that the regular period of these functions belongs to the home space of these spaces. So that is the part where the invariant n prime times the unitary group invariant property of regularization is used here. This is the part where the one of property of regulation is used. And so we can regard this regular period as a linear function in this basis. So, and I computed the local home space of this global home space is 0 for almost all q to the minus g at some unramified places by the twisted local descent of this representation to the small unitary group un plus 2a. So computing this twisted local descent, I showed that the local home space of this global home space is 0 at some unramified places. Then it shows that this global home space is 0, and it shows that this regularized period is 0. So I deduced from this the vanishing lemma. So I personally, if this, I think this is the power of representation theory, because if we do not use the representation theory, then we need to compute this in a very complex and involved way. But using the representation theoretic argument, we can prove this period integral is 0 without much computation. Only use the representation theoretic argument. So the time is up. So I want to I close my talk at this part. So let me summarize the proof. Since in the lemma 1, I decomposed this regularized period of residual Eisenstein series into the sum of these two parts, and I show that this second sum is non-zero, and in the above vanishing lemma, I prove that this regular period of Eisenstein series is always 0. So this part vanishes, and this second part only remains. But I prove that the second integral is non-zero. So it implies the regular period of residual Eisenstein series is non-zero, and it says it claims the existence of residual Eisenstein series, and it says the relevant central L value is non-zero, and it proves the one direction of the GGB conjecture for non-magic Fourier case for square-dimensional unitary group. Okay, I close my talk. Thank you very much.
Thank you, Dr. Jaeho Haan. Are there any questions or comments? Okay, so since we don't have time, we don't have more comments online. Perhaps we finish last session, then ready to close our symposium. And thank you for your interesting long historical talk, Dr. Jaeho Haan, again.
Thank you very much.
Okay, so it's time flies, I should say. And I hope we all enjoyed the 2-day symposium, the CAST International Symposium on Period of Automorphic Forms. I feel that I had a long journey, but very interesting journey. while I had a journey, we met many emerging fantastic ideas from topology, very different area, physics, geometry, of course, algebra, and number theory, of course. So it was a really still interesting journey. First of all, I like to thanks to all participants who stay with us. So far for 2 days. This was on YouTube, so you can listen, you can learn again and again, repeatedly, sing this YouTube. And I think some of the slides are available by speakers' homepage or contacting speakers personally. You can get those slides if you want. Secondly, I like to thank to staff from CAST and the PMI, in particular Seohyuna and Seosanmin for their effort and endless support to run this symposium. And again, thanks to kind support from CAST, the Korean Academy of Science and Technology. And I like to thanks again, my special thanks to all distinguished speakers. Your fantastic, amazing, interesting talks and the presentation lead us the new door in which we, in particular, Professor Sagushin, without his effort, this meeting was not possible. I hope the world is getting better so that all of you can visit Korea and we can really feel your idea together. Thank you very much for all. If there is anyone like to say anything, please welcome. Please do so.
In return, on behalf of all the speakers, I wanted to thank you, Youngju and Sugwoo and CAST for putting this together. It's very important that we keep, communicating in the pandemic, and I really appreciate it.
Well, thank you so
very much
for your generous comment. And then also, let me repeat that maybe this time we have a lot of conjectures from your 3 talks, but maybe next time we can host an in-person conference reporting on results or answers to these conjectures. I hope so. And we might have new speakers as more people get into this game.
Okay, thank you very much. So yeah, like Sogu said, let's have more energy to rush to this new program. Thank you very much and good night.
Thank you so very much. It was wonderful.
Thank you very much.
한재호 박사님, 최도훈 교수님 감사합니다.
감사합니다.
감사합니다. 초청해 주셔서 너무 감사합니다.
고맙습니다.
Thank you all.
Thank you.